Have you ever wondered if everything we know about the origin of the universe is wrong? For decades, we've lived under the comforting canopy of the Big Bang Theory, a single, cataclysmic moment of creation from which everything, from galaxies to atoms to life itself, was born. A model that gave us clarity, timelines, and a framework to understand our cosmic ancestry. But what if it's incomplete? Or worse, wrong? What if the very foundations of modern cosmology are starting to tremble under the weight of new data? As the James Webb Space Telescope began to peer deeper into the universe than anything before it, something unexpected happened. Scientists didn't just see further, they saw anomalies. Galaxies that shouldn't exist. Structures that defy the timeline of cosmic evolution. And light, ancient and redshifted, not behaving as it should. It's not just a shift in data, it might be a shift in reality. But before we continue, subscribe to the channel so you don't miss out on any of these videos. To understand why this is so earth-shattering, let's first journey through what the Big Bang Theory has long claimed. According to this prevailing model, around 13.8 billion years ago, the universe began as a singularity, a point of infinite density and temperature. Then, in a fraction of a second, it began expanding, and over time, matter cooled, condensed, and formed stars, galaxies, and everything we see around us. This theory gained traction because it explained the cosmic microwave background radiation, the abundance of light elements, and the redshift of distant galaxies, which made it appear as if everything was moving away from everything else. But then came JWST, a $10 billion technological marvel launched in December 2021. Its mission? To look further into space, and thus further back in time, than any other observatory before it. The goal was to observe the earliest galaxies and stars, mere hundreds of millions of years after the supposed Big Bang. Scientists expected to see young, chaotic, irregular blobs of matter in the early universe, galaxies in their infancy, still assembling. But that's not what they found. Instead, JWST detected mature, massive, and surprisingly well-structured galaxies existing just 300 to 400 million years after the supposed birth of the universe. Not one or two anomalies, but dozens. These galaxies had the kind of complexity, mass, and shape that should have taken billions of years to develop. Some of them are as large as our Milky Way, if not larger, and feature well-defined disks and spiral arms, structures that according to current models should only form much later in cosmic history. One of the most jarring examples is a galaxy catalogued as Glass C13, which may have formed just 300 million years after the Big Bang. And it's not just small and new, it's big and old. Its size, luminosity, and mass are off the charts when compared to what standard cosmological models predicted for that era. So, how could these galaxies have formed so quickly, and in such organized ways, when the universe was supposedly still in its infancy? It gets stranger. JWST also captured light spectra from these early galaxies. Light that, based on its redshift, tells us not only how far away it is, but also how fast it's moving and how much the universe has expanded since it was emitted. The redshift values were not just high, they were anomalously high. In some cases, the redshift suggested these galaxies existed even before the universe was theoretically old enough to allow such massive structures to exist. Now, if you're wondering whether this could be an error in measurement, the teams involved in these discoveries used multiple cross-checks and instruments to verify the data. And similar results keep pouring in from independent studies. So if the data is correct, it means one of two things: either the early universe formed galaxies in ways we don't yet understand, or the timeline and mechanics of the Big Bang Theory need serious reworking. This brings us to a critical point. Scientists are now grappling with the possibility that the universe may not have expanded as smoothly or as slowly as once thought. Some theorists suggest there could have been earlier periods of hyperaccelerated formation, driven by unknown forces or conditions. Others propose radical alternatives. Maybe the universe never had a singular beginning. Maybe the redshift we see isn't purely the result of cosmic expansion. There are even physicists who argue the universe is much older than 13.8 billion years. That what we thought was the beginning might simply be the latest chapter in a far older cosmic history. Some of these ideas draw from tired light hypotheses, suggesting that the redshift is not a measure of distance or expansion at all, but a gradual loss of photon energy over time as light travels vast distances. But let's not stop there. Because JWST isn't just detecting galaxies, it's also analyzing the atmospheres of exoplanets, the chemical compositions of stars, and the remnants of ancient stellar explosions. And these readings are starting to question other long-standing assumptions. For example, the expected chemical abundances in early galaxies don't always match predictions. Elements heavier than hydrogen and helium, so-called metals, in astronomical terms, are found in higher quantities than models suggest should be possible so soon after the Big Bang. According to conventional cosmology, it takes several generations of stars to create and disperse these heavier elements into space. Yet here they are, baked into ancient galaxies from the very beginning. Then there's the unexpected smoothness of the early universe's structure. According to the Standard Model, the universe started in a highly chaotic, uneven state, with random quantum fluctuations expanded into massive differences in density. These differences then seeded the formation of galaxies and clusters. But the structures JWST is revealing look too uniform, too mature, and too abundant for such a model to comfortably explain. As more data arrives, cosmologists are scrambling. Conferences are being held. Papers are being rapidly written and peer-reviewed. New theoretical models are being proposed. Among them are modifications to the standard lambda CDM model, alternative explanations involving dark energy behaving differently than expected, or even the reintroduction of cyclic universe models, where the universe undergoes endless cycles of birth, death, and rebirth, with the Big Bang merely being a bounce from a previous contraction phase. And what about cosmic inflation, the theory that the universe underwent an unimaginably rapid expansion in the first trillionth of a second after the Big Bang? JWST's observations are prompting a re-evaluation of inflationary models too. If galaxies formed this early, and in such mature forms, it may mean that inflation didn't leave behind the kinds of density fluctuations we thought it would, or that inflation didn't occur the way we imagine. In other words, JWST hasn't just opened a new window to the universe, it may have shattered the glass ceiling of our cosmic understanding. And all this raises a deeply philosophical question: what does it mean if our origin story is wrong? Science evolves through challenge. Theories must be able to accommodate new evidence or give way to better models. And right now, the Big Bang theory is being tested like never before. Not because of ideological opposition, but because of cold, hard data from the farthest reaches of time and space. And here's the twist: this is just the beginning. JWST is still early in its mission. The telescope is expected to continue sending back data for at least another decade. What other mysteries might it reveal? Could it uncover objects even older than our current age of the universe permits? Could it expose relics from an era before the Big Bang itself? Could we discover physical laws that only apply at cosmological scales, laws that break down the elegant but possibly limited principles of general relativity and quantum mechanics? If galaxies existed before galaxies were supposed to exist, if light behaves in ways it shouldn't, and if chemical fingerprints show unexpected stories, then what we're witnessing may not just be anomalies. We might be witnessing the slow, graceful collapse of an old paradigm, and the dawn of a new cosmology. So, if the Big Bang theory, the cosmic cornerstone of modern astrophysics, is now trembling, where does that leave us? It leaves us at the edge of a scientific revolution. But revolutions don't happen overnight. They unfold in layers. Evidence mounts, debates grow heated, paradigms are pushed, and slowly, a new framework begins to emerge from the rubble of the old. One of the key triggers of this paradigm pressure comes from the discovery of ultramassive black holes in the early universe. James Webb has detected galaxies harboring black holes with masses millions to billions of times that of our Sun, existing only a few 100 million years after the Big Bang. This is perplexing. Under our current understanding, black holes grow by accreting matter and merging with other black holes. That process takes time. A lot of time. For black holes to have reached such enormous sizes so early, something doesn't add up. Either they formed from a different kind of seed, something we've never observed, or they started forming before the Big Bang, or at least before our current understanding of cosmic time began. Some researchers are now considering primordial black holes that formed not from stars collapsing, but from ultra-dense regions of the very early universe. But even that idea struggles to account for the sizes we're seeing this early in the cosmic timeline. These are not merely curiosities. They are inconsistencies that, if left unresolved, could spell the unraveling of our entire cosmological model. Then we come to the nature of cosmic redshift itself. One of the foundational pieces of evidence for the expanding universe, and thus the Big Bang, is that light from distant galaxies is redshifted. This means the wavelength of the light is stretched, moving it toward the red end of the spectrum. The standard interpretation is that space itself is expanding, stretching the light as it travels. But there's a competing idea that's being revisited now in light of JWST's data, the tired light hypothesis. Originally proposed in the early 20th century, tired light suggests that photons lose energy as they travel vast distances through space, without the need for the universe to expand. The concept fell out of favor due to a lack of supporting evidence, and because it didn't fit other observations. But now, with the discovery of galaxies that seem too old, and light behaving in unexpected ways, some physicists are taking a fresh look at this alternative. If light loses energy in ways we don't yet understand, perhaps redshift is not the incontrovertible proof of expansion we once believed. Moreover, James Webb is revealing new layers of complexity in cosmic dust and star formation. The expectation was that early galaxies would be relatively dust-free. After all, cosmic dust is formed by the deaths of stars, and in the early universe, there hadn't been enough time for generations of stars to live and die. But JWST has observed an abundance of dust in these young galaxies, implying a stellar life cycle that somehow progressed much faster than we ever thought possible, or that star formation began much earlier than our models allow. This creates a domino effect across cosmological theory. If dust existed earlier, then stars formed earlier. If stars formed earlier, then so did galaxies. And if galaxies existed before galaxies were supposed to exist, the timeline of the Big Bang theory starts to compress uncomfortably. It's like reading the final chapter of a novel in the first few pages. Some have even speculated that the universe may have a completely different structure or origin mechanism. One model gaining attention is the emergent universe model, which suggests the universe had no true beginning, but slowly transitioned from a static state into an expanding one. This model eliminates the need for a singularity and smooths out the paradoxes currently plaguing Big Bang cosmology. Another alternative is the conformal cyclic cosmology proposed by Sir Roger Penrose, which posits that the universe undergoes infinite cycles, each ending in a kind of heat death and beginning again through a new inflationary period. Intriguingly, JWST's high-resolution imaging may eventually provide evidence of patterns or echoes from previous cosmic cycles. And let's not forget the implications for dark matter and dark energy. These mysterious substances, which supposedly make up about 95% of the universe, remain undetected in direct experiments. JWST isn't designed to detect dark matter directly, but its observations of galactic rotation curves and gravitational lensing provide vital clues. If galaxies in the early universe are rotating faster than expected and forming more rapidly, this may require us to rethink what role dark matter plays, or even whether it exists in the form we imagine. A similar rethinking applies to dark energy. If the universe is not expanding uniformly, or at all, then the whole idea of dark energy, a mysterious force causing accelerated expansion, could be a misinterpretation. Perhaps the acceleration is an illusion, a product of our misreading of redshift or time. These aren't fringe ideas anymore. They're gaining traction because the evidence is no longer matching the theory. Let's also look at the cosmic microwave background, CMB, often cited as the crown jewel of evidence for the Big Bang. This faint glow of radiation fills the universe and is thought to be the leftover heat from the Big Bang, stretched out over billions of years. But some researchers now wonder whether the CMB is being interpreted correctly. The JWST doesn't observe in the same wavelengths as the CMB detectors, but the new structural insights from JWST are raising questions about whether the CMB's uniformity is actually a problem for the Big Bang model. The early universe appears too smooth, lacking the degree of fluctuation that would be expected if quantum chaos had really governed the earliest moments. In fact, some simulations now suggest that the universe should be more lumpy than it is. JWST is seeing a universe that seems oddly coordinated, like a symphony that started playing in harmony too early. These harmonies, these alignments of structure and scale, defy the expectation of randomness that quantum fluctuations should have left behind. And this is where we venture into the strangest territory of all, the possibility that the universe has built-in order. Some physicists and philosophers alike are now exploring whether there's a hidden architecture to the cosmos, something deeper than even the laws of physics, perhaps a blueprint or cosmic code operating beneath the surface of all things. If that sounds wild, remember that history is full of such moments. When Newton described gravity, no one had imagined invisible forces acting at a distance. When Einstein described space-time curvature, it revolutionized our understanding of gravity itself. And now, perhaps we stand on the brink of yet another upheaval, brought about by a golden telescope floating in the cold darkness of space. James Webb is not just a telescope. It is a philosopher, a detective. It is forcing us to ask questions we thought were settled, to doubt answers we believed were eternal. And perhaps its greatest gift is not the images it sends back, but the humility it demands. The humility to accept that we might not know where we came from. That the truth is deeper, older, and stranger than anything we've dared to imagine. But what comes next? How do scientists move forward in this brewing storm of discovery and doubt? The next steps will be crucial. New missions are already being proposed to complement JWST, like the Nancy Grace Roman Space Telescope, which will map dark energy with unprecedented precision. Ground-based observatories like the Extremely Large Telescope, ELT, in Chile will join the effort. Meanwhile, theoretical physicists are scrambling to build models that can accommodate what JWST is revealing. Some are working on quantum gravity frameworks that merge general relativity and quantum mechanics. Others are reinterpreting inflation through the lens of holographic principles or multidimensional cosmology. And all the while, JWST continues to peer into the past. Each photon it captures is a whisper from the dawn of time. Each image it returns is a fragment of a puzzle whose final picture may redefine reality itself. Perhaps the most startling realization birthed by James Webb's mission is that our perception of time itself may be fundamentally flawed. If galaxies formed earlier than expected, if black holes reached monstrous sizes far too quickly, then time, at least as we understand it, may not be flowing in the linear, consistent fashion cosmologists once believed. This has prompted a resurgence of interest in alternative time models, including cyclical time, block universe theory, and even the notion that time is an emergent property rather than a fundamental dimension. The block universe model, for example, envisions all moments, past, present, and future, as existing simultaneously, like frames in a film reel. We don't travel through time. Instead, our consciousness experiences slices of it in a fixed order. The implications of such a model, especially when paired with the data from James Webb, are profound. Perhaps the distant galaxies we observe are not relics of a long-gone past, but still active, in a different slice of this cosmic block. Perhaps our notions of causality and evolution are shaped more by perception than by universal law. James Webb has also unveiled something even more mysterious: the unexpected chemical complexity of the early universe. It was long assumed that the first few 100 million years after the Big Bang were dominated by hydrogen and helium, the simplest elements. Heavier elements, like carbon, oxygen, and iron, were believed to form only after the first generations of stars lived and died. But JWST has detected signatures of these heavier elements, sometimes in surprising abundance, in galaxies that are supposed to be only a few 100 million years old. Where did these elements come from so early? Were the first stars far more massive and short-lived than we imagined, enriching the cosmos with complex chemistry in just a blink of cosmic time? Or is something else happening, Perhaps a yet unknown mechanism of element formation that bypasses the stellar process entirely? If such a mechanism exists, it could change not only how we understand the universe's infancy, but also the origin of life itself. Complex chemistry means the early universe may have been far more hospitable to biological precursors than previously believed. That possibility opens yet another can of cosmic worms: life. If the conditions for life appeared earlier than expected, what does that mean for the timeline of biological evolution? Could life, or proto-life, have emerged in a young universe, independently across countless early planets? Could life have been seeded from outside, through panspermia, or even encoded into the very fabric of reality? James Webb is not equipped to detect life directly, but its unprecedented sensitivity allows it to analyze exoplanet atmospheres for biosignatures. Already, it has found signs of carbon dioxide and water vapor on distant worlds. Soon, we may detect methane, oxygen, or even more exotic gases that could hint at biological processes. The more we look, the more the universe begins to resemble something less like a cold, mechanical machine and more like a dynamic, living system, complex, self-organizing, and possibly even self-aware in some unimaginable way. It's not hard to see why thinkers are once again entertaining metaphysical ideas once considered too fringe for science. Concepts like the anthropic principle, which suggests the universe appears fine-tuned for life because it must be for us to observe it, now seem less like philosophical thought experiments and more like real possibilities in the face of JWST's findings. One of the most unsettling implications is that the Big Bang may not have been the beginning of everything, but merely the beginning of our observable region of a much larger and older multiverse. If that's the case, then James Webb may not just be peering into our past, it might be seeing echoes or imprints of other cosmic domains, different universes with different physical laws. These imprints might appear as unexplained cold spots in the cosmic microwave background, or as inconsistencies in the large-scale structure of space. Already, some data has hinted at possible large-scale anomalies, areas where the laws of physics seem slightly off compared to the rest of the cosmos. While still debated, these could be the fingerprints of neighboring universes brushing against our own. If proven, this would utterly rewrite our understanding of existence. The Big Bang would not be the singular event it's been made out to be, but just one of countless bangs across a boundless multiversal landscape. This leads into the speculative realm of brane cosmology and string theory, frameworks that propose our universe is a three-dimensional brane, floating in a higher dimensional space. Collisions between branes could be what we perceive as Big Bangs. If true, then James Webb might one day capture light or gravitational waves from such a collision, an ancient event not at the origin of our universe, but the result of another universe slamming into ours, rippling space and time with it. Gravitational waves themselves are another frontier JWST complements. While it doesn't detect them directly, its sharp vision helps identify the types of cataclysmic events, like black hole mergers, that produce these waves. As these two observational tools, gravitational wave detectors and next-gen telescopes, merge their data, we could soon be triangulating the most energetic events in the universe with incredible precision, revealing not only where and when they occurred, but also challenging how we think about energy, space, and causality. All of this stokes the question, what if the Big Bang theory isn't wrong, but simply incomplete? What if it's just the surface layer of a deeper, more intricate cosmic narrative, one written in codes we've only just begun to decipher? Perhaps the singularity isn't the beginning of time, but a transition, a bridge between states, between cycles, or even between universes. James Webb's data might be pointing us to the notion that the cosmos did not explode into existence, but instead emerged from a prior state, a cosmic womb of sorts. There's a growing class of models that suggest the universe emerged from quantum fluctuations in a vacuum, or from a pre-existing geometric state with no mass or energy, only potential. These are not mystical ideas. They come from respected corners of physics, from scientists grappling with math that leads them beyond the edge of spacetime itself. And that's where we must confront the possibility that the ultimate nature of the universe may be unknowable, not because it's beyond science, but because it transcends the frameworks we currently use to define knowledge. If the very structure of reality is built on something non-local, non-linear, or even conscious, then the James Webb Space Telescope isn't just challenging our understanding of space and time, it's exposing the limits of language, measurement, and logic itself. It's a humbling and exhilarating thought. The telescope was built to look back in time, but what it's really doing is forcing us to look forward, toward new physics, new metaphysics, and new possibilities. We thought we were solving mysteries. Instead, we are unraveling a cosmic riddle whose answer may be forever just out of reach. But that is the beauty of exploration. In searching the stars, we uncover truths not only about the universe, but about ourselves. We are creatures of wonder, shaped by questions. And the greatest question of all, where did it all begin, may have no end. And as the James Webb Space Telescope continues its celestial vigil, orbiting 1,000,000 miles from Earth at the second Lagrange point, it silently collects photons that have traveled billions of years through the dark, expanding fabric of space. Each data point it records is a relic, a whisper from the past, carrying stories that defy our most cherished cosmological doctrines. Among the most haunting of these whispers are the so-called impossible galaxies. James Webb has imaged fully formed spiral galaxies, structures that were once thought to require billions of years to evolve, existing at redshifts corresponding to only 400 to 500 million years after the supposed Big Bang. These galaxies are not small, chaotic, or immature. They are structured, organized, and massive. Some show clear rotation curves, suggesting a level of gravitational coherence that, under current models, should have been impossible in such a young universe. This discovery has sent shockwaves through the cosmological community. According to the Lambda cold dark matter model, the universe was chaotic and devoid of complex structures in its early epochs. The first stars were expected to be massive, short-lived population 3 stars composed almost entirely of hydrogen and helium. They would die quickly, producing heavier elements that would seed subsequent generations of stars. But Webb's observations reveal galaxies with mature populations and chemical compositions inconsistent with this timeline. Moreover, these galaxies are often found in environments that suggest gravitational interactions, mergers, and clustering, all processes that require time. Yet time, according to the Standard Model, should have been in short supply. This discrepancy isn't just a matter of observational error. It implies either our interpretation of redshifts is flawed, or the universe's evolution occurred at a much more accelerated pace than we theorized. Either answer forces us to reconsider the foundational assumptions of modern cosmology. But what if it's not just galaxies that are forming too early, but also supermassive black holes? Webb has peered into quasars, ultra-bright, supermassive black holes at the centers of early galaxies, and found them to be fully formed and actively accreting matter at times when the universe was less than 5% of its current age. Some of these cosmic monsters have masses exceeding 1 billion suns. The formation mechanisms for black holes of such mass, in such a short time frame, remain one of the most pressing unsolved puzzles in astrophysics. Current theories posit that black holes grow by accreting gas or by merging with other black holes, but even under ideal conditions, there shouldn't have been enough time. Could they have formed directly from the collapse of massive clouds of gas, bypassing stellar evolution entirely? That would imply a completely different mechanism at play in the early universe, one not accounted for in current models. Some even speculate these black holes could be primordial, remnants from an even earlier cosmic epoch that predates the Big Bang. This idea introduces the provocative possibility of a pre-Big Bang universe, a cosmos that didn't begin from a singularity but emerged from a prior state of existence. Theories like loop quantum cosmology propose that the universe undergoes a series of expansions and contractions, cosmic bounces, instead of a single explosive birth. Others suggest that our universe is the offspring of a black hole formed in a parent universe, a concept grounded in theoretical models involving higher dimensions and brane cosmology. Here, James Webb's role becomes paradoxical. It was designed to confirm our understanding of the early universe. Instead, it may be revealing a different story, one in which the Big Bang is not a beginning but a transition, a ripple in a larger cosmic tapestry woven across time and space. If the early universe was so complex, so structured, and so chemically rich, then the Big Bang's role may have been more localized than universal. Webb also challenges the homogeneity and isotropy assumptions of the universe. The idea that, on large scales, the universe is the same everywhere and in all directions. Observations have revealed unexpected anisotropies, such as uneven distributions of galaxy types and structures in opposite hemispheres of the sky. While subtle, these asymmetries could point to fundamental issues with the cosmological principle itself, a cornerstone of the Big Bang theory. If the universe is not homogeneous, it might be far older, more complex, or structured by laws we have not yet comprehended. It might contain hidden dimensions, variable constants, or even exhibit signs of engineered design, concepts once considered taboo in scientific discourse, now quietly finding their way into mainstream conversation. Dark matter and dark energy, which together comprise 95% of the universe according to current models, remain entirely undetected directly. Yet we rely on them to make our equations balance and our observations make sense. Webb's precision might help to clarify or even upend our understanding of these enigmatic components. Already, some alternative theories are gaining attention: modified Newtonian dynamics, MOND, scalar field models, or even theories that challenge the very nature of gravity itself. And there's the ever-haunting possibility that reality is not what it seems at all. Quantum mechanics and general relativity, our two most successful theories, are fundamentally incompatible. Webb's contributions could provide data that finally exposes the cracks in one or both. Perhaps space and time are emergent properties of quantum entanglements. Perhaps the cosmos behaves more like a hologram than a three-dimensional object, a view supported by some interpretations of string theory and black hole entropy calculations. This holographic principle, if validated by observations of light bending, cosmic background anomalies, or gravitational lensing, would turn our concept of space inside out, suggesting that all the information in our three-dimensional universe is encoded on a two-dimensional surface, like a cosmic projection. In such a universe, the idea of a beginning becomes ill-defined. There is no bang, only a shift in information. And in the deepest philosophical sense, James Webb's revelations invite us to question what we mean by the word origin. Is the origin of the universe a physical event, a metaphysical transformation, or a perceptual boundary imposed by our observational limitations? Each time we think we've found the beginning, we are presented with clues that hint at something before it. Something beyond. In this way, the James Webb Space Telescope does more than challenge the Big Bang. It challenges the human need for final answers. For singularities. For neat beginnings and tidy ends. It suggests that the story of the universe is more like an unending symphony than a one-note explosion. A cosmic opera that stretches across dimensions, timelines, and perhaps even minds. And as we continue to sift through its data, frame by frame, light wave by light wave, we are reminded of something deeply profound. The more we learn, the less we know. And in that vast unknowing lies the true wonder of the cosmos. As the James Webb Space Telescope continues to peel back the layers of the cosmos, its revelations are not only rewriting textbooks but also challenging the psychological comfort zones of astronomers and cosmologists. The universe, as it unfolds through Webb's mirror, appears far older, more structured, and vastly more mysterious than our prevailing models had prepared us to accept. One of the most disturbing findings comes in the form of the too much light problem. According to the standard cosmological model, the amount of infrared background light in the universe should correspond to the cumulative output of all stars and galaxies since the dawn of time. Yet, Webb's ultra-deep infrared surveys reveal a diffuse glow, an unexpected surplus of light that cannot be accounted for by known galactic sources. This discrepancy is not minor. It suggests either that there are more stars and galaxies than we've ever imagined or that entirely new sources of light are contributing to the cosmic background. What might these sources be? Some have speculated about rogue stars or intergalactic dust reflecting light in strange ways, but others whisper darker possibilities: decaying dark matter particles, or even light leakage from parallel universes. These are not fringe theories anymore. When conventional science fails to explain observation, the boundaries between physics and metaphysics begin to blur. The very idea that energy could be seeping into our universe from an adjacent reality, something string theory permits under certain models, is no longer science fiction but a testable hypothesis. This concept ties into another profound mystery, the arrow of time. Why does time only move forward? The second law of thermodynamics tells us entropy increases, but that's a statistical rule, not a fundamental one. In theory, the equations of physics are time-symmetric. They work just as well backward as forward. So why do we remember the past and not the future? James Webb doesn't answer this directly, but its glimpses of the early universe suggest that time, like space, may not be fundamental. If the structure of space-time emerges from quantum entanglements, as some quantum gravity theories propose, then time itself might be an emergent illusion, tied to the thermodynamic properties of the quantum fields that define our cosmos. And if time is not real in the way we think, what does that say about the Big Bang? What if there was never a bang, in the first place? What if what we interpret as a beginning is simply a boundary, a transition between two different quantum states of the universe? This has profound implications not just for cosmology, but for our very understanding of existence. Adding fuel to the fire, Webb's unparalleled resolution has revealed star clusters and protogalaxies tightly packed in ways that should have created gravitational chaos. Yet these systems appear stable, hinting at physics not yet fully understood, possibly interactions involving dark matter that don't align with our current gravitational theories. Or perhaps our model of gravity itself breaks down under extreme conditions, a possibility that would undermine the entire scaffolding of the Big Bang framework. There's also the haunting suggestion that we may be observing echoes of ancient, long-dead universes, cosmic fossils buried in the microwave background or hidden in the statistical anomalies of galaxy distributions. Some theoretical physicists believe the universe retains a kind of memory, an imprint of previous cosmic cycles. Webb's high-fidelity instruments might just be sensitive enough to detect these whispers from universes long extinguished. These ideas intersect with a growing interest in conformal cyclic cosmology, a theory proposed by Nobel laureate Sir Roger Penrose. He argues that the universe undergoes infinite cycles, each beginning with a Big Bang and ending in a vast, cold expansion. In this model, the end of one universe transitions smoothly into the beginning of another, not through a singularity, but through a kind of mathematical transformation in the shape of spacetime itself. If Webb's data begins to support this model, then the Big Bang is not the birth of everything but merely the latest chapter in an eternal, cyclical story. Yet, for all its power, Webb may also be revealing our limits. Consider the cosmic horizon problem. We can only observe a sphere of space roughly 93 billion light-years in diameter, beyond which light hasn't had time to reach us. This limit means we could be missing entire structures, forces, or laws that govern the cosmos on a truly grand scale. If the observable universe is just a bubble in a much larger multiverse, then our models, based only on what we can see, might be akin to explaining the ocean by analyzing a glass of seawater. And this leads to the anthropic dilemma. Is the universe the way it is because we are here to observe it, or are we here because the universe must inevitably produce observers like us? Webb's insights into cosmic fine-tuning, the delicate balance of constants like the gravitational constant, the strength of the strong nuclear force, and the cosmological constant, only deepen this puzzle. The chances of these constants falling within the narrow ranges that allow for the formation of stars, planets, and life are astronomically small. Some argue this is evidence of design. Others invoke the multiverse, suggesting that countless universes exist, each with different physical constants, and we just happen to inhabit the one that supports life. But Webb's data might eventually tip the scales, offering observational clues that support or refute the existence of other universes. Perhaps through gravitational lensing anomalies, or unexplained cosmic alignments, or even deviations in quantum background fluctuations. And while all these mysteries grow, one stands above them all: consciousness. Webb isn't designed to study the mind, yet it indirectly raises the question of why the universe appears comprehensible at all. Why should a being made of dust, orbiting a mediocre star in a forgotten corner of a galaxy, be capable of unraveling the deepest secrets of the cosmos? Could consciousness itself be a fundamental component of the universe, woven into the very fabric of reality like space and time? Some interpretations of quantum mechanics suggest this might be true, that observation collapses probability waves and brings the universe into a defined state. If so, then our act of peering into the universe is not passive, it is participatory. We are not separate from the cosmos. We are part of it, and perhaps even essential to its unfolding. James Webb, in this light, becomes more than a telescope. It becomes an eye, not just for humanity, but for the universe itself. An eye through which the cosmos can begin to know itself. As we stare deeper into time, maybe we are also looking into the mirror of existence, and perhaps, just perhaps, something is staring back. What if, as some radical thinkers propose, the act of observation, the very process enabled by tools like the James Webb Space Telescope, is not merely gathering information but actually influencing the structure of reality itself? Quantum physics, especially in its Copenhagen interpretation and its more exotic offshoots, implies that the universe does not exist in a fixed, deterministic state until it is observed. Measurement causes wave functions to collapse, realities to crystallize out of probabilities. But what if this principle applies not just to particles, but to the entire cosmos? The implications are staggering. If the universe requires conscious observers to choose a definite reality from a sea of potential ones, then we, and by extension the Webb telescope, are entangled in a cosmic feedback loop. In trying to understand the origins of the universe, we may be playing a role in shaping them. The telescope becomes a philosophical tool as much as a scientific one, a bridge between matter and meaning. Returning to the data, Webb has also thrown a wrench into our understanding of reionization, the era in the universe's early history when light first began to travel freely after the cosmic dark ages. According to the Standard Model, this reionization occurred some 400 million years after the Big Bang, as the first stars and galaxies ignited and bathed the cosmos in ultraviolet light. But the galaxies Webb has observed, some less than 300 million years old, already exhibit characteristics of having emerged from that process. This compresses the timeline for star and galaxy formation even further and undermines our neat picture of a gradual cosmic awakening. In simpler terms, the first stars and galaxies seem to have emerged fully formed, far earlier than they should have. This isn't just unexpected, it's paradigm-breaking. The dark ages of the universe might not have been so dark or so long. If the very notion of a slow, gradual unfurling of light is false, then our understanding of time itself in the early universe must be re-evaluated. This has led some theorists to resurrect discarded ideas like quasi-steady-state cosmology, which posits that the universe did not begin from a single event but has instead undergone continuous matter creation over infinite time. Though this model fell out of favor due to lack of empirical support, Webb's anomalies, these well-formed, high-mass galaxies appearing too early, have made it a subject of serious discussion once more. Another eerie twist concerns black holes. Webb has detected supermassive black holes, millions to billions of times the mass of our Sun, already in place just a few 100 million years after the supposed Big Bang. This makes little sense. According to conventional astrophysics, black holes form from the collapse of massive stars and then grow slowly by accreting matter and merging with others. The sheer size of these early black holes implies that either they formed through some unknown, ultra-efficient mechanism, or they existed before the first stars did, suggesting that black holes may be fundamental components of the cosmos, not mere byproducts of stellar evolution. This has prompted speculation about primordial black holes, a hypothetical type of black hole that may have formed directly from fluctuations in the density of the early universe, possibly even before light itself was released. If these existed, they could also explain dark matter, the mysterious, invisible substance that makes up about 85% of the mass in the universe but has never been directly observed. Could Webb be indirectly detecting a hidden scaffolding of black holes, shaping the cosmos not from the edges, but from within? And yet, with every discovery Webb makes, we are reminded that we may be fundamentally misunderstanding the very fabric of space-time. Einstein's general relativity has passed every test we've thrown at it, but it remains incompatible with quantum mechanics. And while Webb isn't designed to resolve that rift, its discoveries create the very tension points where a new theory, perhaps quantum gravity or string theory, might emerge. One tantalizing clue lies in the anomalies of galaxy rotation and motion. While dark matter has long been invoked to explain the odd behavior of galaxies spinning faster than they should, there's another possibility. Maybe gravity doesn't work the way we think it does on cosmic scales. Modified Newtonian dynamics, MOND, and other alternative gravity theories have long been sidelined, but the sheer weirdness of the Webb findings has given them new life. And then there's the quiet, almost whispered realization that perhaps the cosmic microwave background radiation, the thermal afterglow of the Big Bang, is not a beginning at all, but an echo. Some researchers have proposed that this radiation could be the decayed residue of previous universes, bleeding into our own through some unknown quantum process. If Webb's data can be correlated with unexpected patterns in the CMB, like the so-called cold spot, a region of the sky suspiciously empty of galaxies, it might suggest that we are indeed living in one iteration of many. The eerie symmetry and self-organization that Webb detects in galactic structures also hints at something profound. The laws of physics themselves may evolve over time. This is not just wild speculation. The idea that fundamental constants, like the speed of light or the strength of electromagnetism, might have been different in the early universe is being investigated with growing seriousness. If confirmed, it would demolish the idea of a fixed, immutable cosmic rulebook. More controversially, it might even suggest a form of cosmic natural selection, where universes reproduce through black holes, each new universe possessing slightly different physical laws. Over countless iterations, those universes most capable of generating black holes, and therefore future universes, become more common. In this view, we live not in the only universe, or even a privileged one, but in one that was selected, over eons, for its reproductive success. Webb, without intending to, may be collecting the first data points in support of this staggering idea. As we continue to stare deeper into the abyss, Webb's mirror shows us not just distant galaxies, but the reflected image of our own ignorance. The universe is far more bizarre, more structured, and more ancient than we dared to dream. The Big Bang may yet hold its place in the cosmological pantheon, but it stands increasingly not as an ultimate truth, but as a working model, useful, perhaps, but incomplete. The cracks in its foundation are not signs of failure, but of growth. In their place, new paradigms will emerge, perhaps stranger, more elegant, or more terrifying than we can imagine. And in the silence between stars, the Webb telescope drifts onward, a sentinel of our deepest questions and boldest dreams. It listens. It watches. And as it does, the universe continues to whisper secrets it has held since before time began. Yet, as the James Webb Space Telescope peers deeper, something unexpected is unfolding. Not only are we being forced to reconsider the age and structure of the universe, but we're also confronting a sobering philosophical truth. We may not even know what kind of universe we live in. In one of its more puzzling revelations, Webb has detected an unexpected uniformity in galaxy structures across vast regions of space that, according to the Standard Model, should not have been in causal contact. This ties directly into what physicists call the horizon problem, the question of how regions of the universe separated by enormous distances could appear so remarkably similar in temperature, structure, and density, despite not having had time to exchange information or light. Cosmic inflation, a theory proposed to solve this problem, suggests that the universe expanded faster than the speed of light in a fraction of a second after the Big Bang. This rapid inflation would have stretched space so quickly that it created the illusion of uniformity. But Webb's observations suggest an even greater level of uniformity than inflation accounts for. In effect, the telescope is telling us that the inflation theory might itself be too limited, or that we might be missing an even more fundamental piece of the puzzle. This has led to fringe but fascinating ideas, such as the notion that our entire observable universe is just a bubble within a larger multiverse, and that this bubble interacts with others in ways we're only beginning to detect. There are even mathematical frameworks being proposed where the Big Bang is just a localized event in a much larger, perhaps eternal, cosmic landscape. Some theorists suggest that the cosmic microwave background itself might hold imprints, bruises, from collisions between our universe and others. These would appear as anomalies, cold or hot spots that don't match the rest of the background radiation. While evidence is still inconclusive, Webb's capability to look at distant galaxies with such precision may help us triangulate such patterns, cross-referencing the large-scale distribution of galaxies with known irregularities in the CMB. In another paradigm-breaking turn, Webb has also thrown open questions about the very shape of the universe. Traditionally, the universe has been assumed to be flat, meaning that the geometry of space follows simple Euclidean rules. This was supported by precise measurements of the CMB and large-scale structure. However, recent analyses of galaxy distributions and light bending from gravitational lensing, sharpened to unprecedented resolution by Webb, are hinting that there may be a slight curvature to space. A closed universe would suggest that the cosmos is finite and curved back on itself like the surface of a sphere. In contrast, an open universe would be saddle-shaped and expand forever. A flat universe is the balance point between these two extremes. If Webb's data leans more toward curvature, then our models of eternal expansion or eventual heat death must be revised. It may also suggest that the universe could, one day, recollapse, or that it already has before, in a potentially cyclical model of endless cosmic rebirth. And speaking of rebirth, another twist emerges from Webb's detailed chemical surveys. The telescope has observed surprisingly complex chemistry in early galaxies, heavy elements like carbon, oxygen, and even traces of complex molecules that should not have had time to form under traditional timelines. These elements are typically forged in the hearts of stars and released into space through supernovae. Their early presence means that not only did stars form quickly, but they also lived and died at astonishing rates. This has caused a growing interest in what are being dubbed Population 3 stars, hypothetical first-generation stars made entirely of hydrogen and helium, untainted by heavier elements. These stars would have been massive, luminous, and short-lived. But Webb hasn't conclusively found them yet. Instead, it keeps finding stars and galaxies already rich in metals, raising the possibility that these population 3 stars either formed and died before the galaxies we're observing, or that our assumptions about the nature of the first stars are simply wrong. If these stars burned faster, evolved differently, or collapsed into black holes rather than going supernova, that could also explain the early appearance of supermassive black holes, tying together another loose thread in this tangled web of mystery. Then there's the riddle of time dilation. In an expanding universe, events in distant galaxies should appear to slow down due to the stretching of space. Supernovae, gamma-ray bursts, and other phenomena ought to look like they're happening in slow motion the farther away we observe them. But Webb's observations of certain high-redshift objects do not consistently show this expected time dilation. In some cases, they appear to behave as though they're much closer, or as though the universe hasn't been expanding at the expected rate. This observation has led to renewed interest in tired light theories, where light loses energy through interactions with the interstellar medium rather than due to cosmic expansion. Though once considered fringe and largely abandoned due to lack of supporting evidence, these ideas are being re-examined in light of Webb's startling data. If light loses energy through mechanisms other than redshift, then our entire method of measuring cosmic distance and age could be flawed. We're also confronting the troubling realization that our measurements of the Hubble constant, the rate of the universe's expansion, differ significantly depending on whether we're measuring nearby objects or very distant ones. This inconsistency, known as the Hubble tension, has become one of the most urgent problems in cosmology. Webb was expected to help resolve it, but instead, it may have made the discrepancy even worse. Its precise observations have added more weight to the idea that the early and late universe are expanding at fundamentally different rates, potentially implying a dramatic shift in cosmic physics at some point in time. This opens the door to previously unthinkable ideas. Could dark energy itself be changing over time? Could we be living through a phase transition in the very vacuum of space, where the fundamental constants of nature are shifting under our feet? Or, more chilling still, could the entire observable universe be a simulation, one whose code is being altered as we explore deeper into its architecture? Some theorists point to the uniformity, symmetry, and fine-tuned constants of the cosmos as suggestive of an artificial origin. While speculative, it is not entirely ruled out by Webb's data, and as the telescope continues to uncover deeper and more ordered complexity, this notion gains a strange kind of traction. Even the geometry of space-time itself may be emergent, arising from more fundamental quantum information structures. Concepts like loop quantum gravity and entropic gravity suggest that space, time, and even gravity are not fundamental forces, but consequences of more abstract laws of information theory. Webb doesn't measure these directly, but its observations give us crucial clues, such as how gravity behaves around early, massive structures, or how quantum fluctuations may have seeded galaxy formation. In this context, the universe begins to resemble not a machine, but a mind, a system of relationships, feedback loops, and emergent properties shaped by logic we don't yet understand. It challenges us not only to think bigger, but to think differently. As Webb gathers more data, it also inspires a new generation of thinkers, not just physicists and astronomers, but philosophers, mathematicians, and visionaries, who are stepping up to wrestle with the full scope of its implications. The boundaries between disciplines are dissolving, just as the boundaries between time, space, and matter seem to do under the telescope's unflinching gaze. And in this moment, as we stand on the precipice of cosmic transformation, we are reminded that truth is not a fixed point but a horizon, one that recedes as we approach, luring us ever deeper into mystery. The James Webb Space Telescope may not have disproved the Big Bang, but it has shaken the very foundations upon which that theory stands. It has cast light on the deepest corners of the cosmos, only to reveal more darkness waiting to be understood. And the story is far from over. As the revelations from the James Webb Space Telescope continue to unfold, a new question begins to echo louder than ever. If the Big Bang theory as we know it is flawed or incomplete, what alternative models of the universe might better fit the astonishing data pouring in? This isn't merely a scientific musing, it's a profound shift in how humanity interprets its own cosmic origin story. One such alternative theory gaining traction is the steady-state model, a concept that once competed with the Big Bang and was largely dismissed after the discovery of the cosmic microwave background radiation in 1965. But Webb's unsettling observations, early galaxies too mature, too massive, and too structured, have caused some physicists to dust off this forgotten framework. The steady-state theory posits that the universe has no beginning or end in time. Instead, it continuously creates new matter to maintain a constant average density as it expands. While this idea had fallen out of favor due to a lack of supporting evidence, Webb's challenge to the timeline of cosmic evolution has prompted theorists to explore whether a modified steady-state universe, or a cyclic model, could better explain these ancient, fully formed galaxies existing when the universe was supposedly still a child. Another contender is the Big Bounce theory. In this model, the universe undergoes infinite cycles of expansion and contraction. Rather than emerging from a singular beginning, the universe bounces back from previous collapses. In this framework, the rapid expansion we call the Big Bang could be just the latest in an eternal series of cosmic reboots. Intriguingly, some of Webb's data, particularly the uniformity and structure in early galaxies, could be interpreted as evidence left over from a previous cycle. But what about the cosmic microwave background, the signature piece of evidence supporting the traditional Big Bang? Webb doesn't directly observe the CMB. That's within the domain of radio telescopes like Planck and WMAP. But its high-precision data on early galaxy formation could eventually force a reinterpretation of what we thought the CMB meant. Perhaps what we interpret as a remnant of a hot Big Bang is instead a kind of echo from a previous universe's collapse, or a feature of a larger, more complex cosmic mechanism entirely. Then there's the radical concept of conformal cyclic cosmology, proposed by Roger Penrose. This model suggests that the universe goes through endless cycles, but without traditional bouncing or collapsing. Instead, the infinitely stretched-out future of one universe becomes the Big Bang of the next. Webb's glimpses of highly structured galaxies at unfathomable distances, and the seeming lack of entropy in early cosmic structures, could lend indirect support to this idea, hinting at a deeper continuity in the fabric of spacetime itself. Adding to the complexity is Webb's capacity to detect infrared signals from exoplanet atmospheres, another area that, while not directly related to cosmology, may help redefine our understanding of life's emergence and its place in the cosmic story. In several exoplanetary systems, Webb has already detected unexpected chemical signatures, carbon dioxide, water vapor, methane, and even hints of photochemical hazes. If these signs prove to be biotic, or at least prebiotic, they raise the tantalizing possibility that life is not a rare fluke, but a fundamental feature of the universe. And this returns us to a sobering philosophical dilemma. Are we even capable of understanding the cosmos from within it? Every time we build a better telescope, every time we refine our instruments and peek further into the abyss seems to deepen. Instead of final answers, we find better questions. There's also a growing awareness that our models may be suffering from anthropic bias. We assume the cosmos began in a way we can understand, with laws and constants we can measure, and a timeline that fits neatly into our observational window. But what if our entire perspective is skewed? What if the Big Bang isn't a beginning but a boundary condition, a surface we cannot see beyond, not because nothing lies past it, but because our tools and minds are fundamentally unequipped to penetrate it? Quantum cosmology suggests something even more bizarre. In this framework, the early universe may have emerged from a quantum superposition of many possible states. That is, there was no one universe at the beginning, but a cloud of probabilities that only resolved into the cosmos we observe after the fact. Webb's discoveries challenge us to think not just about space and time, but about probability, observation, and even consciousness itself as potential players in the cosmic narrative. For instance, one line of inquiry now re-emerging is whether consciousness has any role in collapsing the quantum wave function of the early universe. This doesn't necessarily imply a divine mind or human-centric universe, but it does suggest that the observer may be more entwined with the cosmos than classical science has traditionally allowed. If the universe behaves differently when unobserved, as quantum mechanics suggests at microscopic levels, could the act of cosmic observation, via telescopes like Webb, somehow participate in defining the very history we are attempting to uncover? It may sound like science fiction, but respected physicists like John Wheeler have suggested similar ideas under the participatory anthropic principle. In this view, the universe does not merely contain observers, it requires them. The cosmos and consciousness are not separate domains but two aspects of a deeper, unseen unity. This ties eerily into the nature of dark energy and dark matter, which Webb may help demystify. Right now, about 95% of the universe is made up of dark components we cannot directly observe. Dark matter bends light and anchors galaxies. Dark energy drives the universe's accelerating expansion. And yet both are invisible, undetectable in the lab, and possibly made of exotic particles that defy all standard models of physics. Webb's measurements of gravitational lensing and galactic velocities have begun to refine our maps of these unseen forces, potentially challenging our assumptions about how gravity works on cosmic scales. It may be that what we call dark matter is not a substance at all but a symptom of our ignorance, a placeholder for misunderstood gravity, a quirk of warped spacetime, or a sign of extra dimensions we haven't yet discovered. Likewise, dark energy could be a dynamic field, not a constant. Its behavior may evolve over time, implying that the fate of the universe is not fixed. It may not expand forever. It could slow down, reverse, or enter a phase of instability. Webb's continuing observations of supernovae, galaxy clusters, and distant quasars may soon force a redefinition of what dark energy even is. The James Webb Space Telescope is not simply a machine looking at the past. It is a time machine aimed at the deepest mysteries of existence. And with every beam of ancient light it collects, it tears another hole in the curtain of established theory. We are living in a moment of epistemological upheaval. Theories that held firm for decades are now shaking. New ideas, once dismissed, are rising. The very shape, origin, and purpose of the universe are being questioned not in philosophy classrooms, but in the hard data of infrared light patterns, spectral fingerprints, and gravitational distortions. And perhaps that is the greatest mystery of all, not that the universe defies our theories, but that it ever seemed to fit them in the first place. Yet as our theories collapse under the weight of new revelations, we are reminded that science itself is not a static doctrine, it is a living, breathing process. The James Webb Space Telescope, through its silent, ceaseless observations, is essentially forcing humanity to reforge its cosmological narrative from the ground up. What we once believed to be settled, such as the Big Bang as the singular origin of everything, is now entering a phase of profound scrutiny. Let's examine one particularly striking implication of the Webb data: the idea that time itself may not be what we think. If the early universe already contained mature galaxies, massive black holes, and structured star systems, then the notion of a smooth progression from simplicity to complexity is thrown into chaos. What if time is not linear on a cosmic scale? What if our measurement of age, distance, and expansion are being distorted by assumptions baked into the very models we use to interpret the data? In traditional cosmology, redshift is a cornerstone. It's the measure of how much a galaxy's light is stretched by the expansion of the universe. The higher the redshift, the further and older the object. But Webb is showing us galaxies at extreme redshifts that simply shouldn't exist in their observed state. These galaxies are too bright, too massive, too organized. This forces some physicists to question whether redshift is a purely cosmological phenomenon at all. Could it instead be partly intrinsic, caused by unknown properties of light or space-time? There is precedent for this line of thinking. The late Haltenarp spent his career cataloging anomalous redshifts, galaxies and quasars that appear physically connected despite vastly different redshifts. He proposed that redshift may not always indicate distance or velocity. While his ideas were marginalized for decades, Webb's new data has resurrected interest in these anomalies. If intrinsic redshift plays a role, then much of our cosmic map may need to be redrawn. Distances would be uncertain. Ages would be unreliable. The universe, as we interpret it, could be a kind of optical illusion, a hall of mirrors in which light bends, stretches, and transforms in ways we haven't yet accounted for. This, of course, circles back to the instruments themselves. The James Webb Space Telescope operates in the infrared, a wavelength invisible to human eyes but crucial for peering through cosmic dust and into the farthest reaches of space. In doing so, it has opened up previously hidden regions of the cosmos, revealing galactic cores, star nurseries, and planetary systems shrouded in veils of gas and dust. Among Webb's many surprising finds are the ancient galaxies with unexpectedly high metallicity. In the standard Big Bang timeline, heavy elements, like carbon, oxygen, and iron, should be rare in the early universe because they are formed in multiple generations of stars. Yet Webb has observed galaxies teeming with these elements when, by our models, only first-generation stars should exist. This implies that multiple cycles of star birth and death occurred far earlier than expected, compressing eons of cosmic evolution into a cosmic blink. The implications are staggering. Either the universe evolved much faster than we think, or our understanding of stellar life cycles is flawed. Perhaps stars formed differently under the extreme conditions of the early universe. Or perhaps, as some physicists propose, the speed of light or the rate of nuclear reactions may not have always been constant. If constants can vary, even slightly, across time or space, then our entire framework of physics would need reworking. Fundamental forces like gravity, electromagnetism, and the strong nuclear force could have behaved differently in the past. This isn't wild speculation. Some cosmologists are actively researching varying constant models. Webb's data might just provide the empirical push these ideas need to move from theory to mainstream. And it's not just the grand-scale structure of the universe that's being shaken. Even at the scale of planetary systems, Webb is revealing strange phenomena. For example, some exoplanet atmospheres show unexpected heat signatures, suggesting internal energy sources not explained by their star's radiation alone. Others exhibit chemical compositions inconsistent with models of planet formation. Could this be a clue to an entirely new class of physics operating on planetary scales? Some propose that dark matter, traditionally thought to cluster in halos around galaxies, might also influence planetary systems in subtle but measurable ways. Others speculate about unknown forms of energy or particle interactions yet to be discovered. Meanwhile, Webb's observations of black holes are redefining our timeline for their formation. The discovery of supermassive black holes, billions of solar masses, at redshifts above 10 is particularly jarring. These black holes appear only a few 100 million years after the Big Bang, yet current models can't explain how they grew so quickly. Theoretical astrophysicists are now scrambling to come up with new mechanisms for rapid black hole formation, ranging from direct collapse of massive gas clouds to the possibility of primordial black holes that formed during the earliest moments of the universe. Some of these ideas border on the speculative, but they are grounded in hard data. Webb has made the observations. The burden now lies with theory to catch up. It's also worth noting that this is not the first time a new observational tool has reshaped cosmology. The Hubble Space Telescope revealed that the universe is expanding at an accelerating rate, leading to the discovery of dark energy. But Webb is different. It's not merely refining the picture, it's showing us that we may have been looking at the wrong picture all along. In this light, the Big Bang Theory, once hailed as the definitive origin story, may ultimately be remembered as a stepping stone. A useful approximation. A rough sketch of a far more complex and beautiful truth. And yet, even as the old theories crumble, a deeper awe emerges. For in questioning the Big Bang, we are not merely unraveling a scientific theory. We are reimagining our place in a living, dynamic, perhaps eternal cosmos. A universe that may not have had a beginning, but rather always was, and always will be, cycling, evolving, remembering, forgetting. We do not yet know what new cosmology will rise from these ruins. But it is certain that we are in the midst of a paradigm shift, a revolution not of ideology, but of insight. A moment when telescopes become time machines, and data becomes prophecy. And the James Webb Space Telescope, silent and tireless in the void, is the oracle of this new cosmic age. And as this oracle continues to peer into the most ancient corners of existence, it feeds us riddles wrapped in photons, riddles that challenge our very language for describing reality. What do we call a universe that doesn't begin in a bang, doesn't expand as expected, and defies the boundaries of time as we understand it? Even the concept of causality, where one event leads logically to another, comes under scrutiny when faced with the anomalies Webb has uncovered. For instance, in several high redshift observations, galaxies appear to be gravitationally interacting with one another despite the apparent lack of time or space for such interactions to occur. This is not just surprising, it borders on impossible in the current cosmological framework. Could this mean that the structure of space itself is different in the early universe? Or are we witnessing the projection of higher dimensional phenomena into our limited 3D understanding, much like a shadow misrepresenting the true shape of the object casting it? There are models in theoretical physics, such as string theory and brane cosmology, that suggest our universe may be a slice of a higher dimensional reality. These models predict that interactions can occur between dimensions, or that what we see as expansion may be an illusion caused by multidimensional geometry unfolding. Perhaps, then, the Webb telescope is seeing the imprint of such hidden dimensions, galaxies arranged not in our expected web, but in patterns dictated by a deeper order. This idea brings us back to the foundational assumptions we've made since Edwin Hubble's first discovery of the expanding universe. That redshift equals distance, that cosmic microwave background, CMB, radiation is the echo of a singular beginning, and that gravity is the ultimate architect of large-scale structure. Webb's data is not merely stretching these assumptions, it's burning holes straight through them. Consider the mysterious alignment of galaxies observed by Webb over vast distances. These alignments hint at coherence across scales where random distribution was expected. If galaxies billions of light-years apart appear oriented in a specific way, then either some unknown cosmic mechanism is coordinating them, or our entire interpretation of scale and perspective is flawed. Now let's entertain one of the more controversial theories gaining traction in the wake of Webb's revelations, that the universe may not be expanding at all. This radical idea turns redshift from a measure of distance into a kind of evolutionary marker. Instead of galaxies moving away from us, their light could be changing as it travels, affected by the properties of space itself, or by an interaction with a medium we do not yet understand. In this view, redshift might be akin to aging, not motion. Galaxies further away in time might not be further away in space, but simply younger in a universe where location and time are inseparable facets of a more fluid cosmic reality. This would upend everything. It would render the Big Bang an observational illusion, an artifact of interpreting dynamic light in a static framework. Instead of a universe born in an instant of explosive energy, we may live in a universe with no beginning, no singularity, just infinite transformations. But let's not forget the cosmic microwave background, long considered the smoking gun of the Big Bang. How could that be explained without a singular origin? Some theorists suggest the CMB could be the thermal residue of a much older, perhaps eternal, universe. Others propose that the CMB is not cosmic at all, but local, generated within a vast galactic halo or plasma structure around our own corner of the universe, misinterpreted as a universal signal. James Webb hasn't yet directly observed the CMB. It wasn't built to, but its impact on how we interpret that ancient radiation is already profound. If the early universe doesn't look primitive, chaotic, or slowly forming, but instead structured, metallic, and coherent, then what really caused the CMB? And more crucially, how many of our assumptions about the background universe are the result of incomplete data? These aren't idle speculations. Serious astrophysicists and cosmologists are writing papers re-examining fundamental concepts. Some are resurrecting ideas once dismissed as fringe, tired light theories, quasi-steady-state cosmologies, plasma cosmology. Others are looking for entirely new physics, modifications of gravity, or theories where time behaves like a quantum particle, capable of jumping, reversing, or superimposing. This is the thrilling chaos of a revolution. And it's not just happening in the academic papers, it's unfolding in real time with each new image from Webb. Every frame brings with it more questions than answers. Why are so many galaxies so compact yet so massive? Why is the distribution of mass and light in these systems inconsistent with predictions from cold dark matter models? Why are there seemingly mature galactic disks at redshifts where turbulence and fragmentation should dominate? We're seeing the cosmos not as a slow unfolding of order from entropy, but as a roaring orchestra that began with harmonies already in place. The tempo is off, the notes too precise for a random origin. Something fundamental has been missed. Even time dilation, expected to be visible in the light curves of supernovae and gamma-ray bursts, hasn't been definitively observed where it should be. If the universe is expanding, then events billions of light-years away should appear stretched in time due to the expansion of space. But Webb's precise instruments may be telling us otherwise, again hinting at a problem not with our tools, but with our assumptions. So what do we do with all this? We rewrite. We rethink. We unlearn. The James Webb Space Telescope was not just designed to look further, it was built to reveal the unseen. In doing so, it has made clear that the universe is stranger than we dared imagine, more complex than we hoped, and far more mysterious than we were prepared to accept. And that's not a failure of science, it's science at its finest. We are now at the edge of an intellectual frontier, one where the old maps are no longer accurate, and the stars themselves may not be what they seem. Webb is not the end of the story, it is the call to a new chapter. One in which the universe is not a puzzle with one solution, but a symphony of shifting truths and evolving understanding. This is the moment when science becomes philosophy, when data becomes myth, when reality stretches so far it touches the sublime. And somewhere, in the depths of space, the James Webb Space Telescope continues to watch. And as it watches, it transmits back more than just data. It delivers revelations, wrapped in silence, carried across cosmic time. The photons it captures left their origins billions of years ago, yet they arrive in our present, whispering truths that were once unknowable. This unfolding is not just observational, it's existential. It demands that humanity recalibrate its deepest narratives about who we are, where we came from, and what we are a part of. Because if the James Webb Space Telescope is indeed proving that the Big Bang Theory, our most widely accepted origin story, is incomplete, or even incorrect, then we are living in an era not just of discovery, but of mythological collapse. It's the death of a modern creation story, and the birth of something uncharted. Let's revisit the very heart of the standard cosmological model, the lambda CDM model, which rests on the idea of a singular beginning, the Big Bang, the presence of cold dark matter, CDM, and dark energy, lambda. Every element of this model is being questioned under Webb's piercing gaze. Cold dark matter was introduced to explain the gravitational behaviors of galaxies and clusters that couldn't be accounted for by visible matter alone. It was also essential to simulations that modeled the growth of structure in the early universe. But Webb's observations show galaxies forming far earlier and more completely than these models predicted. That discrepancy is not minor, it's monumental. If dark matter truly shaped the early universe, its footprint should be everywhere. Instead, the structures we see often imply a faster, more organized assembly that doesn't match the predicted patterns of gravitational clumping over time. Some physicists are now questioning whether dark matter even exists in the form we thought. Could it be that gravity itself behaves differently over large distances? Modified gravity theories, once pushed to the margins, are re-entering mainstream conversation. These theories suggest that gravity might not be a constant, but an emergent or variable force that behaves differently in different contexts. If that's true, the very geometry of the universe could be wildly different from what we believed. Then there's dark energy, the mysterious force thought to be accelerating the universe's expansion. It was proposed to account for observations of distant supernovae that appeared dimmer than expected. But again, Webb's ultra-precise instrumentation could be providing new explanations. What if those supernovae aren't farther away due to acceleration, but due to misinterpretations of light behavior over time? What if dark energy is not a substance or force at all, but the result of a false assumption about time, distance, or light propagation? These are the foundational cracks that Webb is exposing, and they go even deeper. Take the idea of cosmic inflation, a theoretical faster-than-light expansion immediately following the Big Bang. Inflation was introduced to solve several key problems in Big Bang cosmology, such as the horizon problem and the flatness problem. But it has always been a patch, a speculative event tacked onto the model to make the equations work. Now, if the Big Bang itself is being questioned, inflation becomes not just uncertain, it becomes unnecessary. And that opens a wild frontier of possibilities. Some physicists and cosmologists are now seriously entertaining cyclic models of the universe. These posit that the cosmos goes through endless cycles of expansion and contraction, big bangs followed by big crunches, then rebirth. In such models, our current expansion is just one breath in an eternal rhythm. But even these cyclical models are beginning to morph under Webb's influence. What if the cycles are not mechanical but informational? That is, what if the universe is more like a quantum computation engine, processing entropy, refining structure, and passing information from one epoch to the next through non-material means? Some theories suggest black holes might act as bridges between these cycles, not as endpoints, but as transformers of reality, filtering and transmitting quantum information across cosmic epochs. James Webb may not be observing black holes in this function directly, but it is seeing the early signatures of supermassive black holes at astonishingly high redshifts, where they shouldn't exist. These colossal objects, with masses millions or even billions of times that of our Sun, appear when the universe was supposedly only a few 100 million years old. According to standard theory, there simply hasn't been enough time for them to form through the gradual collapse of matter. Unless black holes form through entirely different mechanisms in the early universe. Some theorists propose direct collapse models, where massive clouds of gas bypass the star formation stage and collapse straight into black holes. Others suggest that these early black holes are remnants of a previous cosmic cycle, born not from stars but from the collapse of primordial quantum fields, an idea that links quantum mechanics, general relativity, and thermodynamics in ways we're just beginning to imagine. Each of these possibilities carries enormous implications, not just for astronomy, but for the nature of time, space, and reality itself. And they are being resurrected from the margins of theoretical speculation into the mainstream of scientific discourse, driven by the sheer volume and audacity of Webb's data. Yet with every new answer, 1,000 new questions bloom. For instance, why do certain deep-field images show no sign of the expected Lyman break, an absorption feature that should be present in high-redshift galaxies if early starlight is being absorbed by neutral hydrogen? Could this mean the intergalactic medium was ionized far earlier than expected, or that our interpretation of high-redshift absorption features is flawed? Or why do we see light signatures in supposedly primitive galaxies that resemble those from mature stars and complex chemical processes? Are stars forming earlier and faster than we thought, or is stellar evolution itself different in the early universe? Even the nature of time might need redefinition. In quantum gravity theories like loop quantum gravity and causal set theory, time is not a smooth river but a sequence of discrete events, a granular phenomenon. Webb's observations of early galaxies appearing out of sync with expected timelines may hint that cosmic time itself is layered or emergent, not continuous. Imagine a universe where time is not a background parameter, but a substance that can curve, fragment, or even bleed backward in rare conditions. In such a cosmos, Webb's images are not snapshots of then, but clues to the multifaceted nature of now. And it gets stranger. Some scientists are beginning to speculate whether we are inside a simulation, not in the metaphorical sense, but in a real, operational sense where the universe is the product of informational rules, akin to a vast, evolving codebase. Under this model, what Webb is observing might be the boundaries or seams of that simulation, data structures that appear anomalous because they are computational shortcuts or visual compressions of something too complex to render fully. It's a radical idea, but not one without growing traction. Because the deeper we look, the more it seems reality itself may be an emergent property of something deeper, information, consciousness, or an unknown form of physical logic. And through it all, the James Webb Space Telescope continues to record, continues to beam its findings back to Earth, untouched, unjudging, unyielding. It does not know the myths we've built. It does not care for our models or theories. It simply reveals. And in that revelation, we are given the greatest gift, the chance to wonder again. The chance to rewrite the origin story. The chance to gaze into the abyss and say, "We do not know, but now we begin to ask the right questions." We are not at the end of cosmology. We are at its beginning. And so, as the James Webb Space Telescope carves open the heavens and brings ancient photons into focus, we're forced to confront a stunning possibility, that what we thought was the beginning might not be the beginning at all. Maybe the Big Bang wasn't the singular origin of all things, but merely a transitional phase in a much larger, much older cosmic story, one with hidden chapters that we are only now starting to glimpse. In fact, some of the most paradigm-shattering implications of Webb's data lie in its ability to peer not just into deep space, but into deep time. Because light takes time to travel, the farther away we look, the further back in time we see. When Webb gazes 13.5 billion light-years into the distance, it's actually seeing light that left its source 13.5 billion years ago. In essence, we are witnessing the baby pictures of the universe. And yet, these baby pictures don't look like babies. They look fully grown. Galaxies appear too developed, too structured, too massive, and too chemically rich for the cosmic age in which they supposedly existed. This is not a minor hiccup in the data. It's a potential falsification of a model that has defined modern cosmology for over half a century. Let's pause on that for a moment. For decades, we've operated on the assumption that after the Big Bang, the universe went through a rapid inflationary period, followed by gradual cooling and the formation of the first atoms, stars, and galaxies. The timeline was thought to be fairly well understood. The first stars ignited around 100 to 200 million years after the Big Bang. Small galaxies followed, and then over billions of years, larger structures assembled through mergers and accretion. But now Webb is showing us fully formed galaxies existing just 300 to 400 million years after the Big Bang, some with disc-like shapes, bulges, and even spiral arms, features we thought took billions of years to emerge. Some of these galaxies are as massive as the Milky Way. That's not just surprising, it's astonishing. It implies that the processes of star formation, chemical enrichment, and galactic organization happen on timescales far faster than current physics can explain. And that's not all. Spectroscopic analysis by Webb reveals that many of these early galaxies are rich in heavy elements, what astronomers call metals. In cosmic terms, metals include everything heavier than hydrogen and helium. These elements are forged in the hearts of stars and spread into space through supernova explosions. Their presence in early galaxies implies that multiple generations of stars must have already lived and died, again, far too early if the Big Bang model's timeline is to be believed. It's as if we opened an ancient tomb expecting to find the fossils of primitive organisms, and instead discovered skyscrapers, libraries, and spaceports. This is not just a tweak to an equation. It's a cosmic upheaval. And it's driving a scientific renaissance of sorts. Theoretical physicists, cosmologists, and astronomers are rushing back to the blackboard, re-evaluating foundational concepts. Some are proposing alternative cosmologies that dispense with the Big Bang entirely. One such idea is the emergent universe model, where the universe had no beginning, but instead existed eternally in a quasi-static state before slowly transitioning into the expansion we observe today. In this view, the Big Bang wasn't a birth, it was a phase change, like water turning to steam. Others advocate for bouncing cosmologies, where the universe undergoes a cycle of expansions and contractions. In these models, a previous universe collapsed in on itself, a big crunch, followed by a big bounce, that initiated our current expansion. Some bouncing models are even supported by quantum gravity frameworks that eliminate the need for a singularity, meaning, there never was an infinitely small, infinitely dense point from which everything exploded. But perhaps the most provocative implication of Webb's discoveries is the possibility that time itself is not linear, nor absolute. What if the reason we're seeing galaxies too early is because our concept of time breaks down at cosmic scales? In certain interpretations of quantum cosmology, time is not a fundamental property, but an emergent one, something that arises only within certain frameworks. If this is true, then Webb might be showing us that the universe is not older than we thought, but that our understanding of before and after needs a total overhaul. This opens the door to truly mind-bending possibilities. Could we be looking at ghost galaxies from a previous cycle of the universe, somehow imprinted onto our own? Could quantum entanglement be connecting regions of space-time in ways we don't yet understand, causing echoes from past cosmic epochs to appear in our present observations? The James Webb Space Telescope has given us the tools to ask these questions not just philosophically, but scientifically. Its suite of infrared instruments can peer through cosmic dust, detect the faintest glimmers of ancient starlight, and analyze the composition of galaxies that existed when the universe was less than 1 billion years old. And with every pixel of data it sends back, the narrative of the Big Bang grows more uncertain. Even among mainstream cosmologists, a quiet revolution is stirring. Some now suggest that the Big Bang was never a singular event, but a smoothed-out transition in a much vaster quantum landscape. Others speculate that our observable universe is merely a bubble in a frothing multiverse, each bubble governed by different physical laws, different timelines, and different histories. If that's the case, then our universe's apparent beginning might be an illusion, just the start of our local story, but not the story of reality itself. And here's where it gets existential. Because if the James Webb Space Telescope is capable of falsifying the Big Bang model, then it's doing more than just changing science. For too long, modern science has operated under the illusion that we were nearing a theory of everything. That soon, all mysteries would be solved, all equations balanced, all particles discovered. But now, thanks to Webb, we are realizing that the cosmos is not a puzzle to be completed, but a tapestry still being woven. And we are threads in that tapestry. So we watch, we wait, and we wonder. Because as far as Webb is concerned, this is only the beginning. We are witnessing the rebirth of cosmology, not the end of it. As the James Webb Space Telescope continues to gather light that has traveled for over 13 billion years, we are not merely looking backward in time, we're opening a window into dimensions of reality that we never expected. The telescope, with its unprecedented resolution and infrared capability, is not just a better lens, it's a disruptive force, a harbinger of a scientific revolution. Every image it sends back is not only beautiful, but deeply subversive. Each fuzzy red dot, each spiral traced in ancient photons, is a silent rebellion against the stories we've told ourselves about the cosmos. Consider this: some of the galaxies discovered by JWST appear too large and too structured to have formed in the time available. That's not a margin of error issue. That's a core assumption under threat. In the standard lambda CDM model, our best mathematical description of the universe, structures are supposed to form hierarchically, small galaxies first, which then merge into bigger ones. But Webb is seeing massive galaxies at redshifts corresponding to a time when the universe was just a few 100 million years old. This doesn't just suggest fast galaxy formation, it suggests something entirely different than our accepted model allows. Either the rate of structure formation was radically faster, or our entire framework needs updating. This discrepancy has led many scientists to say what was once unthinkable, that the Big Bang model, as it currently stands, may no longer be enough. And it isn't just about galaxies. The James Webb Space Telescope has also begun probing the composition of exoplanet atmospheres, star-forming regions, and even the light signatures of distant quasars. These investigations might seem unrelated at first, but they all point to the same underlying issue. Our cosmological model might be broken not just at the edges, but at the foundation. Some of the more shocking suggestions proposed by physicists in light of JWST data include modifications to dark matter behavior, radical reinterpretations of time, and even new physics operating in the early universe that we have not yet discovered. One particularly fascinating possibility is that gravity itself may behave differently in the early universe than it does today. Modified gravity theories, like MOND, modified Newtonian dynamics, or emergent gravity, are now being taken more seriously, as traditional explanations struggle to reconcile the data with the expected distribution and density of matter. And what if the Big Bang was just a convenient misinterpretation? The model assumes the universe expanded from a hot, dense state. But maybe what we thought was a bang was a slow unfolding from an entirely different kind of structure, perhaps a quantum vacuum fluctuation, a multidimensional transition, or a ripple in a much grander cosmic sea. One rising idea in theoretical circles is that the Big Bang wasn't the start of space-time, but rather the emergence of our patch of it. Some physicists have proposed that what we call the Big Bang is merely a boundary event, like the skin of a bubble in an eternally inflating cosmos, part of a broader multiverse. In this view, other Big Bangs are occurring constantly in a foamy sea of universes, each with their own timelines, laws of physics, and matter content. If so, Webb isn't just looking at our past, it may be revealing the fingerprints of this multiverse, etched subtly in the cosmic microwave background or the distribution of matter. And Webb's infrared eye is perfect for this task. By peering into the darkness, it's catching whispers of what came before, odd alignments in galaxy clusters, unusual voids, strange concentrations of energy, and anomalies in temperature distributions that defy neat explanations. But even if we don't embrace the multiverse theory, there's something else, something perhaps even more shocking. What if our definition of beginning is fundamentally flawed? In classical physics, we assume time has a direction and an origin. But in quantum cosmology, time may emerge only after certain conditions are met. There are models, like the no-boundary proposal from Stephen Hawking and James Hartle, that suggest the universe didn't have a beginning at all, but transitioned from a timeless quantum state into classical spacetime as we know it. In these models, the universe doesn't start with a bang. It simply becomes. This becoming is smooth, continuous, and directionless at its genesis. Time, as we experience it, emerges only after the transition is complete. Webb's discoveries, such as galaxies existing too soon, fit unnervingly well with these interpretations. So we are left with a breathtaking possibility. The universe may not have a beginning in the way we once thought. There may have been no singularity, no explosive moment, but instead an elegant unfolding from a realm beyond time. And as the telescope continues to refine its deep-field observations, we might find even more evidence to support this. Already, astronomers are analyzing light curves, star populations, and galactic shapes with the hope of detecting not just what's there, but what's missing. If certain galaxies seem anomalously old, or contain heavy elements that shouldn't be present, or appear distributed in patterns that contradict our inflationary models, the implication is clear. Our map of the universe is wrong. Not just incomplete, wrong. And this, in itself, is profoundly exciting. Because every time a scientific model breaks, reality peeks through. When Copernicus displaced Earth from the center of the cosmos, people reeled. When Darwin suggested that humans were not divine creations but evolved beings, societies resisted. When Einstein bent space and time into curves, Newton's absolutes crumbled. And now, with the James Webb Space Telescope, we are standing on the edge of another great upheaval. The Big Bang is not a dogma. It's a model. One that served us well. But science progresses by questioning even its most cherished ideas. And in Webb's golden mirrors, reflecting the earliest starlight, we see not certainty, but challenge. It's almost poetic. We launched this telescope to confirm our theories, to sharpen the picture. And what we got instead was a puzzle so vast, so strange, and so beautiful that it may take generations to unravel. And that's the point. Because the greatest gift of the James Webb Space Telescope isn't just data. It's humility. It reminds us that the universe is under no obligation to make sense to us. That the cosmos is not a solved riddle, but a living question. And as long as we keep looking up, we'll keep asking it. And so, the question remains, if the James Webb Space Telescope is quietly tearing at the fabric of the Big Bang model, what lies on the other side of the unraveling? The evidence continues to pile up, not just the impossibly early galaxies, but also their structural maturity. Galaxies observed at redshifts of 10 and beyond, which corresponds to less than 500 million years after the presumed Big Bang, aren't just diffuse clouds of gas and dust. Many of them appear as fully formed spiral galaxies or exhibit a dense central bulge, features that are hallmarks of long-term evolutionary processes. According to standard cosmology, these processes should require billions of years to develop. But here they are, formed and glowing, in what should have been the cosmic dark ages. This isn't a tweakable detail. It's a cosmic paradox. And it's not alone. The JWST has also observed high-mass black holes that seem far too large for their age. Under the Big Bang model, black holes form from the collapse of massive stars and gradually grow over time through accretion and mergers. Yet JWST has spotted quasars and active galactic nuclei powered by black holes with masses in the range of hundreds of millions to billions of solar masses, when the universe was only 5% of its current age. That's like finding an adult elephant in a kindergarten class. The numbers simply don't add up unless some form of rapid, exotic formation process is in play, one we haven't accounted for. These discoveries challenge the timeline of cosmic history itself. Standard cosmology relies on a scaffolding of epochs: the inflationary epoch, the recombination era, the dark ages, the reionization period, and so on. Each has a predicted timescale and set of physical events. But JWST is finding evidence that these boundaries might be blurred or completely misplaced. The onset of reionization appears more complex, less homogeneous, and possibly earlier than expected. The presence of dust, metals, and structured star systems in the supposedly primitive universe implies that nuclear fusion and stellar life cycles had to occur at warp speed, defying expectations. And then there's the issue of cosmic smoothness. The cosmic microwave background (CMB), the remnant radiation from the early universe observed by missions like COBE, WMAP, and Planck, is remarkably uniform. Too uniform, in fact. To explain this, the inflationary theory was proposed, a tiny fraction of a second after the Big Bang, the universe underwent exponential expansion, smoothing out inhomogeneities. But what if this inflationary period never happened? What if the universe was born already smooth, or smoothed itself out in a different, unknown way? JWST can't directly see the CMB. It's not designed to detect microwave frequencies, but it can detect the relics of those early processes. The first stars, the large-scale structure of matter, the distribution of galaxies across vast distances. And the story it's beginning to tell doesn't align perfectly with the one written by inflation theory. Some cosmologists now believe we may be looking at a big adjustment moment in theoretical physics. Not quite the total collapse of the Big Bang paradigm, but a recognition that its edges are fraying. Maybe the Big Bang wasn't a bang at all. Maybe it was a bounce, where a previous universe collapsed and rebounded into this one. Or perhaps it was an emergence from a timeless quantum foam, as described by loop quantum cosmology or string theory's higher-dimensional brane collisions. In the bounce model, for example, the universe undergoes eternal cycles of contraction and expansion. The high-energy densities that mimic a bang are really just the turning point between a previous cosmos collapsing and a new one forming. This model allows for the universe to be much older than it appears, giving those early galaxies time to evolve in a pre-expansion phase. In that case, JWST isn't revealing paradoxes, it's revealing the fingerprints of a cosmic memory older than the bang. The implications of this are staggering. It would mean our universe has no absolute beginning, only phases. What we perceive as the beginning is merely one frame in an infinite loop. Entropy resets, structures dissolve and reform, and time as we know it becomes cyclical. Some researchers, like Roger Penrose with his conformal cyclic cosmology, have even suggested that information could pass from one eon to the next, imprinted subtly in radiation patterns or black hole residues. And the James Webb Space Telescope may be the first instrument sensitive enough to spot those imprints. Think of it, our deepest philosophical questions: where did we come from? Is there a before the beginning? Is time infinite? Are now within the grasp of empirical observation. JWST is no longer just a telescope. It is a philosopher's eye, staring into the void and returning with secrets. But even as we explore these radical theories, the scientific community is split. Some argue for caution. Just because a theory is under strain doesn't mean it should be discarded. History is littered with beautiful ideas that buckled under the weight of new data. The key is not to jump to conclusions, but to expand our framework to accommodate the new information. That may mean refining the Big Bang, not rejecting it. Others, however, are more revolutionary. They see JWST's data not as minor discrepancies, but as the beginning of a seismic shift. They argue that physics has become too comfortable with patching its models rather than rewriting them. Dark matter and dark energy, still not directly detected, were themselves inserted as fixes. Inflation was added to smooth the bumps. Are we really understanding the universe, or just retrofitting our equations to match the sky? And this brings us to a deeper, perhaps more disturbing question: are we finally approaching the limits of the scientific method when applied to cosmology? We can build better telescopes. We can simulate with more powerful computers. But the further we peer into the past, the more theoretical we must become. At some point, our observations stop being confirmations and start becoming interpretations. The data is real, but its meaning depends on our framework. Change the framework, and the meaning changes. This is why the James Webb discoveries are so important, not because they provide final answers, but because they force us to question our assumptions. They expose the scaffolding we didn't realize we were standing on. And in doing so, they open the door to new paradigms. What if, in the coming decades, we move away from the Big Bang entirely? What if schoolchildren in the future learn about the bounce, or the emergence, or the infinite multiverse, not as fringe ideas, but as the new orthodoxy? It has happened before. The shift from geocentrism to heliocentrism, from Newtonian gravity to relativity, from a static universe to an expanding one. We are living through the next great shift. And perhaps, one day, We will look back at the James Webb Space Telescope not just as an engineering marvel or a triumph of international collaboration, but as the instrument that broke the sky open, that shattered our cosmic illusion, that dared to look further than ever before, and found not confirmation, but transformation. The telescope still has years of life ahead. More data, more mysteries, more discomfort, but also more wonder. It reminds us that science is not about being right. It's about being willing to be wrong, gloriously, courageously, and creatively wrong, in the pursuit of truth. And in that pursuit, the stars are not the limit. They're just the beginning. If the James Webb Space Telescope, JWST, has taught us anything, it's that the universe does not yield its secrets easily or quietly. With every new observation, every unexpected signal captured in the deep infrared, we're not just uncovering new cosmic truths, we're unearthing a mounting crisis in cosmology. And this crisis isn't merely academic. It's existential. The standard cosmological model, known as lambda cold dark matter, has long held as the prevailing explanation for the evolution of the universe. It combines general relativity, cosmic inflation, the Big Bang theory, and dark components like dark matter and dark energy to form a coherent narrative. Yet, the more JWST peers into the ancient past, the more the edges of this model begin to blur. The universe doesn't seem to be playing by the rules we've written for it. One of the most profound cracks in the model emerges from something deceptively simple: size. The size of early galaxies, to be precise. In lambda cold dark matter, the formation of galaxies is thought to be a slow, hierarchical process. Small structures merge to form larger ones, taking billions of years to create the massive galaxies we see around us today. But JWST is observing galaxies just a few 100 million years after the supposed Big Bang that are not only massive but also surprisingly compact and dense. These aren't fluffy, nascent systems just beginning to clump together. These are massive, mature entities, filled with stars, dust, and heavy elements. They're too big too early. And their size isn't the only problem. Their shape is another. The cosmic morphology problem has taken center stage. Many of these early galaxies don't appear chaotic or misshapen, as one would expect from something still assembling. Instead, they show signs of disc-like structures, even spiral arms in some cases. These features suggest long-term stability and rotational equilibrium, qualities that simply shouldn't exist at such a young cosmic age. The Big Bang model doesn't forbid early structure formation entirely, but it does place clear statistical constraints on how often and how extreme such structures can be. And yet, JWST is not finding rare outliers. It's finding many of these galaxies. They are not the exception, they are the rule. This implies that our predictions of the early universe are fundamentally flawed. But if these galaxies existed so early and in such numbers, how did they form so quickly? One possibility is that the cooling processes in the early universe were far more efficient than previously believed, allowing gas to collapse into stars and galaxies faster. Yet this raises further problems. Where did the heavy elements come from so rapidly? These elements are forged in stars over long periods and then dispersed by supernovae. But JWST sees signs of chemical maturity, dust and metals, within hundreds of millions of years. Again, it's not impossible, but it's deeply implausible within current models. This chemical maturity also raises the stakes regarding the timing of the first stars. The first generation of stars, known as population 3 stars, are thought to have formed from pristine hydrogen and helium shortly after the universe cooled. These stars were massive, short-lived, and crucial for seeding the cosmos with heavier elements. And yet, direct evidence of population 3 stars remains elusive. Instead, JWST is showing us galaxies that already appear to have population 2 stars, those that contain metals and dust. It's as if the first stars came and went before we had the chance to see them, leaving only their chemical footprints behind. That footprint leads us to yet another enigma: cosmic dust. JWST's infrared capabilities make it especially good at detecting dust-rich regions. But it's finding this dust, abundant and widespread, in galaxies that, again, shouldn't have had enough time to produce it. Dust formation is a slow process. It requires multiple generations of stars to live, die, and release their enriched guts into interstellar space. So how is there so much dust so soon? To make matters more complicated, JWST's deep field observations also suggest that the distribution of galaxies across vast cosmic distances may not align with predictions made by the Standard Model. The number of bright galaxies, their spacing, and their mass distributions all appear to challenge the expected structure formation patterns. Some researchers are now proposing that the dark matter halo framework, the invisible scaffolding upon which galaxies supposedly formed, might not be sufficient to explain these early findings. Which brings us to perhaps the most uncomfortable question: what if dark matter doesn't behave the way we think it does? Or worse, what if it doesn't exist at all? Dark matter has never been directly detected. It was introduced to explain discrepancies in galaxy rotation curves, gravitational lensing, and large-scale structure formation. But it remains hypothetical. If JWST is finding that early galaxies defy dark matter-based formation models, then maybe the problem isn't with the galaxies. Maybe it's with our assumptions about the invisible. Alternative theories of gravity, such as modified Newtonian dynamics, MOND, or emergent gravity, have long challenged the need for dark matter. Perhaps JWST is giving them new relevance. And what of dark energy, the mysterious force accelerating the universe's expansion? That too is built into lambda-cold dark matter, represented by the Greek letter lambda. While JWST doesn't measure expansion rates directly, its observations contribute to the broader debate known as the Hubble tension. This is the growing mismatch between the local measurement of the universe's expansion rate, using supernovae and Cepheid variables, and the value derived from early universe observations, such as the cosmic microwave background. JWST's high-precision data on distant supernovae and galaxy clustering may end up tipping the scale on this tension. If the discrepancy holds or widens, it could imply that the expansion rate of the universe is not constant or that new physics is at play, perhaps a breakdown of general relativity on cosmic scales, or the influence of time-varying dark energy. As these cracks in the Standard Model deepen, a new school of thought is beginning to gain traction. What if our entire conception of time and cosmic chronology is flawed? Some theorists now entertain the idea that the speed of light, or other constants, might have been different in the early universe. A varying speed of light could explain the rapid formation of structures, the uniformity of the cosmic microwave background, and even eliminate the need for inflation altogether. It sounds radical, but in a universe this strange, maybe radical is the new rational. Then there's the possibility that redshift, the cornerstone of our cosmic distance ladder, is being misinterpreted. Redshift is assumed to be a product of space expanding. The farther away a galaxy is, the faster it appears to be moving away, stretching its light toward the red end of the spectrum. But some alternative theories suggest redshift could have other causes: intervening matter, gravitational fields, or intrinsic properties of light. If redshift isn't purely cosmological, then our entire map of the universe could be distorted. Such ideas are, of course, speculative. But speculation is the engine of science. Without it, we stagnate. JWST is a mirror. Not just to the cosmos, but to ourselves. It shows us what we thought we knew, what we missed, and what we dared not imagine. It's proving that the cosmos is not a finished book, but a living manuscript, still being written, still full of blank pages and twisted plots. And the deeper it looks, the more it seems we are only at the prologue. The instruments aboard JWST, its near-infrared camera, NIRCam, mid-infrared instrument, MIRI, and near-infrared spectrograph, NIRSpec, aren't just tools. They are keys unlocking doors we didn't even know existed. They are helping us detect exoplanet atmospheres, peer through dense cosmic dust, and study the birthplaces of stars and planets. They are allowing us to measure redshift with unprecedented accuracy, to dissect the chemical composition of galaxies billions of light-years away, and to ask new questions we hadn't yet learned to phrase. The revolution has only just begun. And with each revelation, the cosmos whispers a truth louder than any theory. It is stranger than we dreamed, deeper than we feared, and more beautiful than we ever dared to hope. As we press deeper into this new cosmic frontier, it's important to understand that the implications of JWST's discoveries ripple far beyond the technicalities of astrophysics. They challenge the very foundation of how humanity comprehends its place in the universe. The Big Bang Theory, for nearly a century, has been our cosmic origin story, an elegant narrative that explained everything from the primordial soup of particles to the galaxies spinning across space. But now, with JWST's data pouring in, cracks are appearing not just in the details, but in the very fabric of that story. One of the most jarring implications of JWST's observations is the possibility that the universe might be older, or at least more complex, than the Big Bang timeline suggests. The Big Bang posits a singular explosive event approximately 13.8 billion years ago, from which space, time, and matter all emerged. The early universe was hot, dense, and expanding rapidly, eventually cooling enough for atoms to form and stars to ignite. But JWST has revealed galaxies so large and chemically evolved at epochs less than 400 million years after the Big Bang that they seemingly had no time to form according to our current models. This raises an uncomfortable question. Could these galaxies have existed before the Big Bang? Or perhaps, is the Big Bang a misinterpretation of cosmic phenomena, an incomplete chapter in a far grander cosmic saga? Some theoretical physicists are now revisiting alternative cosmologies, including cyclic universe models, where the universe undergoes infinite expansions and contractions, big bangs followed by big crunches, repeatedly over cosmic time. In such models, structures from previous cycles might have survived or influenced the subsequent universes, which could explain why JWST is seeing unexpectedly mature galaxies so soon after the last bang. Similarly, there is growing interest in the idea of a multiverse, a collection of multiple, possibly infinite, universes, each with different physical laws and histories. If our universe is just one bubble in a cosmic foam, then perhaps what JWST is observing is evidence of interactions between universes, or even remnants of other universes bleeding through the cosmic veil. These ideas are highly speculative, but they gain traction in light of JWST's findings that resist explanation within the standard Big Bang framework. Then there is the horizon problem, which was initially one of the Big Bang's key puzzles. It refers to the uniform temperature of the cosmic microwave background (CMB) radiation despite causally disconnected regions. Cosmic inflation was proposed to solve this, a rapid, exponential expansion right after the Big Bang, smoothing out irregularities. But JWST's observations suggest the presence of mature cosmic structures that challenge how quickly and smoothly inflation could have occurred. If inflation didn't happen as we think it did, or at all, it would require rewriting not just cosmology but the foundations of particle physics and quantum gravity. New physics might emerge, reconciling gravity with quantum mechanics in ways that radically alter our understanding of space and time. JWST's insights into early galaxies also cast a new light on dark energy, the mysterious force pushing the universe's accelerated expansion. While dark energy remains enigmatic, JWST's ability to track the formation and distribution of galaxies across time could provide critical clues about whether dark energy's strength has varied or behaves differently than predicted. If dark energy is dynamic rather than constant, our models for the universe's fate, whether it will expand forever, collapse, or tear itself apart, may need drastic revision. Another intriguing mystery relates to the so-called cosmic dawn and epoch of reionization, when the first stars and galaxies lit up the cosmos and reionized the neutral hydrogen that filled space. JWST's deep observations into this era are revealing complexities unseen before. The timing, speed, and mechanisms of reionization appear more varied and chaotic than previously thought, suggesting that the first luminous objects might have formed in bursts or under environmental conditions that current models cannot yet simulate accurately. The discovery of massive black holes in the early universe adds yet another layer of complexity. JWST has detected quasars powered by supermassive black holes with masses billions of times that of our Sun, existing when the universe was less than 1 billion years old. The question is, how did such enormous black holes grow so quickly? Traditional models suggest a slow accretion process, but these observations imply alternative growth mechanisms. Perhaps primordial black holes formed from density fluctuations shortly after the Big Bang, or exotic processes involving dark matter interactions. Moreover, JWST's unprecedented resolution allows astronomers to examine the chemical fingerprints of these ancient galaxies. Spectroscopic analysis reveals not just hydrogen and helium, but also heavier elements like carbon, oxygen, and nitrogen, essential for life as we know it. This indicates that stellar processes responsible for element formation were well underway much earlier than theorized, possibly even challenging the timeline of the first star's appearance. All of these findings have sparked heated debates within the scientific community. While some propose tweaking the lambda cold dark matter model, others argue that a wholesale revision or replacement is necessary. This may usher in a new era of cosmology where alternative theories such as quantum cosmology, string theory, or emergent spacetime gain prominence. JWST is also influencing the search for extraterrestrial life. By studying exoplanet atmospheres with exquisite sensitivity, it can detect biomarkers like water vapor, methane, or oxygen, indicators of potential habitability, or even life. The early universe's rapid chemical evolution hints that the ingredients for life could have formed sooner than expected, expanding the timeline and scope for the emergence of life. JWST's discoveries are reshaping our cosmic narrative. The Big Bang Theory, while elegant and explanatory for decades, is now confronted with data that challenge its completeness and assumptions. This doesn't mean the Big Bang is definitively wrong. Science rarely discards theories outright, but it does mean that our understanding of the universe's origin, evolution, and structure is evolving dramatically. As JWST continues its mission, it promises to deepen this cosmic revolution, unraveling more mysteries and revealing the astonishing complexity of the universe. The telescope's findings beckon humanity to rethink its place in the cosmos, inspiring both awe and humility before the vast unknown. And so, as we stand at this crossroads, looking through the lens of the James Webb Space Telescope, we glimpse a universe far stranger and more wondrous than ever imagined, a universe that invites us to question, explore, and dream anew. Beyond the immediate shockwaves JWST's discoveries send through cosmology, there lies a profound philosophical and existential ripple effect. Humanity's story has long been entwined with the narrative of cosmic beginnings, the Big Bang providing a neat, almost mythic origin for everything we see and experience. Yet now, with the emerging contradictions, the story is shifting from certainty to mystery, from a single beginning to possibly an endless cosmic tapestry. One striking consequence is how JWST's data forces us to reconsider time itself. The conventional Big Bang model ties time's inception directly to the singularity event, the moment, zero, when all space, time, and energy burst forth. But if JWST is revealing galaxies that are too old or too developed to fit that timeline, we must ask, does time truly have a beginning? Or might time be cyclical or multidimensional, extending beyond our current comprehension? Some modern theories suggest time may be emergent, not fundamental. In such views, time arises from deeper quantum processes, potentially without a clear start. This would align with some interpretations of quantum gravity and string theory, where our familiar space-time fabric is just one layer in a more complex, higher-dimensional reality. JWST's challenges to the Big Bang push these theoretical ideas from speculative fringes towards scientific urgency. JWST's findings also breathe new life into the quest to unify general relativity and quantum mechanics, the holy grail of physics. The early universe, with its extreme densities and temperatures, is the natural laboratory for such a theory of quantum gravity. If the Big Bang singularity is not a true beginning, but a transition or phase shift in a grander cosmic cycle, then understanding these transitions demands breakthroughs in physics beyond the standard model. Observations from JWST can provide indirect clues, through the structure, distribution, and composition of ancient galaxies, that might help unlock this mystery. Furthermore, JWST's insights challenge the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. The discovery of mature galaxies and structures that appear unexpectedly clumped or unevenly distributed at early times may imply that the universe is more heterogeneous than previously believed. This could have ramifications for how we interpret cosmic microwave background data and the very nature of cosmic expansion. On the matter of dark matter and dark energy, JWST provides new avenues to explore these enigmatic components that constitute about 95% of the universe's total energy budget. Dark matter, which does not emit or absorb light but exerts gravitational influence, has long puzzled astronomers. JWST's high-resolution imaging and spectroscopy enable unprecedented mapping of dark matter's effects on early galaxy formation. This can refine models about its nature, potentially distinguishing between competing candidates like weakly interacting massive particles, WIMPs, axions, or more exotic entities. Dark energy, the mysterious force accelerating cosmic expansion, may also be better constrained by JWST's observations of galaxy clusters and supernovae at great distances. If dark energy's properties vary over time, as some models propose, JWST could detect subtle deviations from the expected expansion rate, challenging the cosmological constant assumption. These discoveries would profoundly influence predictions about the universe's ultimate fate. One cannot overstate the revolutionary potential of JWST in understanding black holes, especially the supermassive ones that lurk at the centers of galaxies. Their early formation and rapid growth remain one of astrophysics' biggest puzzles. JWST's ability to peer through cosmic dust and gas allows detailed studies of their host galaxies and environments, shedding light on how these monstrous entities influence galaxy evolution and vice versa. This interplay affects star formation rates, galactic structure, and the distribution of matter in the universe. Moreover, JWST's detection of complex organic molecules and early chemical enrichment hints at a universe that became biologically interesting much sooner than expected. This accelerates astrobiological timelines and compels us to consider that life's building blocks might have been widespread throughout cosmic history, potentially even before Earth's formation. Consequently, JWST elevates the search for life beyond Earth into a question that spans cosmic epochs, not just planetary timescales. Another intriguing frontier opened by JWST relates to gravitational waves and their sources. While JWST itself is not a gravitational wave detector, its observations complement data from detectors like LIGO and Virgo by pinpointing the astrophysical environments where these waves originate, merging black holes, neutron stars, and other cataclysmic events. Understanding these environments in the early universe helps reconstruct cosmic history and tests models of gravity under extreme conditions. As JWST continues its mission, it also challenges us to rethink the methodology of science itself. The telescope's capacity to generate vast, complex datasets requires advances in data analysis, artificial intelligence, and collaborative global research networks. It exemplifies how modern science is as much about managing information and interdisciplinary cooperation as it is about individual discovery. JWST's revelations remind us of the humility and wonder intrinsic to scientific inquiry. The telescope's images, breathtaking vistas of cosmic dawn, star nurseries, and ancient galaxies, invite a profound reflection on humanity's place in the universe. They inspire not only scientists but also philosophers, artists, and all who seek to understand the grand tapestry of existence. The James Webb Space Telescope stands as a beacon at the edge of human knowledge, illuminating a cosmos more mysterious and complex than the neat narratives we once held. By challenging the Big Bang Theory and opening new questions about time, space, matter, and life, JWST ushers in an era of cosmic renaissance. It invites us to embrace uncertainty and curiosity, forging a path toward deeper truths about the universe and ourselves. This journey is far from over. With each new observation, JWST expands the horizon of what we know, and more importantly, what we have yet to discover. The universe's mysteries are vast, and now, more than ever, we are poised to explore them with eyes and minds wide open, ready to be astonished. As the James Webb Space Telescope continues to peer deeper into the cosmos, its unprecedented clarity and sensitivity are beginning to reveal phenomena that not only question the Big Bang's timeline but also hint at possible alternative origins of the universe. One of the most compelling puzzles relates to the early abundance and maturity of galaxies observed by JWST. Galaxies that appear massive, chemically evolved, and well-structured mere hundreds of millions of years after the supposed Big Bang defy the standard cosmological models that predict a much slower process of galaxy formation and evolution. This anomaly suggests that the universe's initial conditions, or the physics governing its earliest moments, might be different than previously thought. Perhaps the universe did not begin with a singular explosive event but emerged from a more gradual or cyclic process. Some physicists propose that the universe underwent a bounce from a previous contraction phase, avoiding a true singularity and allowing structures to survive across cosmic cycles. This cyclic, or ekpyrotic, model contrasts with the singular beginning of the Big Bang, and could explain the early presence of mature galaxies JWST detects. In parallel, the idea that our universe is just one bubble in a vast multiverse gains indirect support. If multiple universes exist, each with varying physical constants and histories, JWST might be witnessing evidence of collisions or interactions between these universes, imprinting unusual structures and galaxy formations onto our cosmic landscape. This theory, while speculative, provides a framework that could accommodate the unexpected findings without dismissing the overall cosmic evolution narrative. Another fascinating implication of JWST's discoveries relates to the nature of dark matter, which remains one of the biggest enigmas in physics. JWST's observations of galaxy rotation curves and gravitational lensing in early galaxies offer new clues about how dark matter clusters and interacts with normal matter in the young universe. Some results challenge the conventional cold dark matter model, suggesting the presence of warm or self-interacting dark matter that behaves differently than previously assumed. This could dramatically alter our understanding of cosmic structure formation and evolution. Similarly, JWST's ability to analyze exoplanet atmospheres with exquisite precision opens the door to a new era in astrobiology. By detecting biosignatures such as oxygen, methane, and water vapor in distant worlds, the telescope could identify planets with the potential for life, reshaping humanity's understanding of its place in the cosmos. The earlier-than-expected chemical enrichment observed in ancient galaxies implies that the ingredients for life may have been present much earlier in cosmic history than we thought, increasing the chances that life exists elsewhere. Moreover, JWST's detection of complex organic molecules in interstellar clouds and protoplanetary disks points toward a universe rich in the chemistry necessary for life. These discoveries suggest that the building blocks of life are widespread, perhaps universal, and that the emergence of life may be a common cosmic phenomenon rather than a rare Earth-bound event. JWST's insights also extend to black holes, particularly the supermassive black holes powering early quasars. Their rapid formation challenges current theories of black hole growth, which rely on slow accretion over billions of years. JWST data hint at alternative formation scenarios, including the collapse of massive primordial gas clouds or direct collapse black holes, which would allow these behemoths to emerge quickly in the young universe. Furthermore, JWST's observations of the cosmic dawn and epoch of reionization reveal a universe transitioning from darkness to light in complex and uneven ways. The reionization process, during which the first stars and galaxies ionized the neutral hydrogen-filling space, appears to have been patchy and prolonged. This challenges simpler models and suggests diverse sources contributing to this transformative epoch, including early galaxies, quasars, and possibly exotic objects. As the telescope continues its mission, it also enables the study of gravitational waves' astrophysical origins by characterizing environments of merging black holes and neutron stars. Combined with ground-based gravitational wave detectors, JWST's data help reconstruct the violent events shaping the cosmos and test fundamental physics under extreme conditions. On a broader scale, JWST's revelations compel scientists to rethink fundamental assumptions like the cosmological principle, which assumes uniformity and isotropy on large scales. The uneven distribution and maturity of early cosmic structures hint at a more complex and varied universe, with profound implications for cosmological models and interpretations of cosmic background radiation. These challenges extend to the mysterious dark energy, responsible for accelerating cosmic expansion. JWST's detailed observations may detect variations in dark energy's properties over time, questioning the cosmological constant assumption and altering predictions of the universe's fate, whether it will expand forever, collapse, or face a big rip. In essence, the James Webb Space Telescope is not just a new eye on the cosmos, it is a revolution in our understanding of the universe. By challenging the Big Bang Theory's assumptions and timelines, revealing new astrophysical phenomena, and offering fresh data on fundamental cosmic components, JWST pushes the boundaries of science and philosophy alike. Its discoveries inspire awe and curiosity, reminding us that the universe is far stranger, richer, and more mysterious than our current theories can capture. As JWST continues to unveil the cosmos's secrets, it invites humanity to explore deeper questions about our origins, existence, and destiny among the stars. This ongoing journey promises not only scientific breakthroughs but also a profound expansion of human perspective, forever altering how we see ourselves in the grand cosmic story. The James Webb Space Telescope's ongoing observations continue to reshape our understanding of cosmic history, pushing the boundaries of what we thought possible and challenging the very framework of the Big Bang Theory. One of the most provocative revelations involves the apparent existence of surprisingly massive and evolved galaxies at epochs so close to the universe's inception that their maturity contradicts the gradual growth expected under standard cosmological models. According to the conventional Big Bang timeline, the earliest galaxies should have been small, irregular, and relatively primitive, as the universe was still young and matter had not had sufficient time to coalesce into large, structured systems. Yet JWST's data reveals galaxies that are not only massive but also rich in heavy elements, metals forged in the cores of earlier generations of stars, indicating rapid and complex star formation processes had already occurred. This evidence suggests that galaxy formation mechanisms might be far more efficient or fundamentally different than previously believed. This observation has profound implications. It forces astrophysicists to revisit or expand models of galaxy formation and evolution, considering alternative processes such as accelerated star formation fueled by exotic dark matter interactions, or early black hole activity triggering rapid growth. Some theorists propose that primordial density fluctuations, the initial irregularities in the distribution of matter, may have been larger or differently distributed, speeding up the formation of complex structures. Such findings also intersect intriguingly with ideas about cosmic inflation, a hypothesized exponential expansion in the universe's earliest fractions of a second. If the initial conditions that seeded structure formation differ from inflationary predictions, or if inflation operated differently, the timeline for galaxy maturation might be compressed, or entirely new physics might be required. JWST's data thus serves as a crucial test bed for inflationary models and alternative early universe scenarios. Another major frontier opened by JWST involves the detection and analysis of primordial chemical signatures. The chemical composition of early galaxies, including unexpectedly high abundances of elements heavier than hydrogen and helium, challenges the simplistic view that only the earliest stars could synthesize such elements. This hints at a more nuanced stellar population history and suggests the existence of massive, short-lived stars, population 3 stars, that enrich the interstellar medium rapidly before disappearing. Detecting direct evidence of these first-generation stars is a key objective, and JWST's infrared sensitivity is vital, as it can peer through cosmic dust and over vast distances to capture their faint signatures. Beyond astrophysics, JWST's discoveries ripple through fundamental physics. For instance, the discrepancies between observed galactic evolution and theoretical predictions raise questions about the nature and behavior of dark matter. The standard cold dark matter paradigm, positing slow-moving particles that clump gravitationally, may need refinement or replacement by alternative models incorporating warm or self-interacting dark matter. JWST's high-resolution maps of galaxy shapes, rotations, and distributions provide essential data to test these hypotheses. In parallel, JWST's observations can constrain dark energy models, the mysterious force driving the universe's accelerated expansion. If the properties of dark energy vary over time or space, a concept known as dynamical dark energy, JWST might detect subtle deviations from predictions based on a cosmological constant. Such findings would revolutionize our understanding of the universe's fate and the underlying physics governing its expansion. JWST also opens new avenues in black hole research, particularly regarding the early formation of supermassive black holes observed as quasars in the young universe. Their existence less than a billion years after the Big Bang suggests rapid formation processes that challenge standard accretion models. JWST's ability to observe these early quasars and their host galaxies in detail allows scientists to explore alternative theories, such as direct collapse black holes forming from massive gas clouds or mergers of primordial black holes. Moreover, JWST has brought renewed attention to the epoch of reionization, the period when the first luminous objects ionized the neutral hydrogen filling the cosmos. Observations indicate this transition was complex and extended over hundreds of millions of years, involving multiple sources and regions evolving at different rates. Understanding this epoch is critical for reconstructing the universe's timeline and the emergence of the cosmic web of galaxies and clusters. In the realm of astrobiology, JWST's capabilities herald a new age in the search for life beyond Earth. By analyzing exoplanet atmospheres with unprecedented detail, JWST can detect potential biosignatures, such as water vapor, oxygen, methane, and other organic molecules, on planets orbiting distant stars. The early appearance of chemically rich galaxies implies that the essential ingredients for life could have been widespread early in cosmic history, potentially increasing the likelihood of life elsewhere. JWST's discoveries also challenge the assumption of a homogeneous and isotropic universe on large scales, known as the cosmological principle. The observed irregularities and mature structures at early times suggest the cosmos might be more varied and complex than this principle assumes, forcing a re-examination of cosmological models and interpretations of cosmic microwave background radiation. The James Webb Space Telescope stands as a transformative instrument that not only challenges the Big Bang Theory's detailed predictions but also opens new windows into the universe's fundamental nature. Its findings push humanity toward deeper questions about cosmic origins, the nature of matter and energy, the emergence of complexity and life, and the ultimate fate of the cosmos. As JWST continues its mission, it invites us to embrace uncertainty and to expand the horizons of knowledge, reminding us that the universe is a vast, dynamic mystery that will continue to inspire wonder and discovery for generations to come. The James Webb Space Telescope, JWST, has not only transformed our understanding of cosmic history but also illuminated profound mysteries that challenge the foundations of cosmology as we've known it. One of the most provocative puzzles lies in the very early universe, the first few 100 million years after what the Big Bang Theory posits as the origin of everything. Traditional Big Bang cosmology suggests that the universe began roughly 13.8 billion years ago in a hot, dense state, rapidly expanding and cooling over time. The earliest stars and galaxies formed gradually as matter clumped under gravity, with primitive galaxies evolving slowly before maturing into the vast structures we observe today. But JWST's powerful infrared vision has revealed galaxies that appear astonishingly massive, complex, and chemically evolved far earlier than this timeline allows. These ancient galaxies, some formed less than 300 million years after the supposed Big Bang, appear fully formed with mature star populations and significant amounts of heavy elements. The presence of these metals indicates multiple generations of stars had already lived and died, enriching their surroundings, a process thought to require much more time. This early maturity contradicts predictions from standard models of galaxy formation, suggesting that either the universe evolved far more rapidly or that some fundamental assumptions about its beginning may be incomplete or flawed. Scientists have begun exploring several intriguing possibilities to explain these findings. One hypothesis proposes that the universe might have undergone phases before the Big Bang as we understand it, involving cycles of contraction and expansion, known as bouncing cosmologies. In such models, the universe's birth was not a singular, unique event but a transition from a previous phase, which could explain the early complexity observed. This idea challenges the classical concept of a singular origin and opens the door to a deeper, possibly infinite cosmic history. Another possibility is the existence of a multiverse, a vast ensemble of universes, each with its own physical laws and histories. JWST's observations could hint at interactions or remnants from such parallel universes, manifesting as unexpected structures and early galaxy formation. While speculative, this concept aligns with some interpretations of quantum mechanics and string theory and invites a radical rethinking of our cosmic context. JWST also challenges the nature of dark matter and dark energy, two mysterious components that together make up about 95% of the universe's total mass energy content but remain poorly understood. The telescope's precise mapping of early galaxies and their gravitational effects provides crucial data to test whether dark matter behaves as a cold, collisionless particle, as currently believed, or exhibits more complex, self-interacting properties. Such variations would profoundly affect how structures formed and evolved. Similarly, by analyzing the rate of cosmic expansion through detailed studies of early universe objects, JWST may reveal whether dark energy is truly a cosmological constant, or a dynamic force that changes over time. Detecting any such variation would revolutionize physics, possibly requiring new fundamental theories beyond Einstein's general relativity. In addition to these cosmological impacts, JWST advances the study of the first stars, known as population 3 stars. These stars, composed almost entirely of hydrogen and helium, are theorized to be massive, short-lived, and responsible for producing the universe's first heavy elements. Direct detection of population 3 stars has eluded astronomers until now, but JWST's infrared sensitivity might finally allow us to observe their signatures, filling a crucial gap in understanding cosmic chemical evolution. JWST's influence also extends to the enigmatic supermassive black holes found at the centers of early galaxies. Their rapid growth, visible as quasars glowing billions of times brighter than our Sun, remains a major puzzle. Standard black hole growth models through slow accretion fail to explain their size so soon after the Big Bang. JWST's observations support alternative formation scenarios, such as the direct collapse of massive gas clouds or primordial black hole mergers, potentially rewriting black hole astrophysics. Beyond purely physical phenomena, JWST's discoveries carry profound philosophical and existential implications. If the Big Bang is not the ultimate beginning or if the universe is part of a larger multiverse, what does that mean for humanity's understanding of existence? These findings inspire not just scientific inquiry but a deeper reflection on our place in a potentially infinite cosmos, filled with mysteries yet to be uncovered. Moreover, JWST's ability to characterize exoplanet atmospheres revolutionizes the search for life beyond Earth. The detection of biosignature gases on planets orbiting distant stars, possible indicators of microbial, or even complex life, raises profound questions about the uniqueness of life in the universe. Coupled with the early chemical richness observed in ancient galaxies, JWST's data suggests that the ingredients for life might have been widely available much earlier than anticipated. As the telescope continues its mission, each new discovery invites fresh questions, pushing the limits of human knowledge. The Big Bang Theory, while remarkably successful, is increasingly seen as an incomplete chapter in a far more complex cosmic story. JWST stands at the forefront of this transformation, guiding us toward a new era where the universe's deepest secrets may finally be revealed. In this unfolding saga, humanity's role is both as observer and participant, exploring the cosmos with ever more sophisticated tools, expanding the horizon of what we understand, and embracing the profound mystery that defines existence itself. The James Webb Space Telescope is more than a machine. It is a beacon of discovery, illuminating the dark corners of space and time, and inviting us all to ponder the grand tapestry of the universe with wonder, and awe. As JWST continues to send back a flood of unprecedented data from the distant cosmos, it becomes clear that the universe is far stranger and more intricate than the simplified version we once embraced. The telescope's revelations compel scientists to reconsider the assumptions underpinning the Big Bang Theory, not to discard it outright, but to refine it, or even replace it with new paradigms that better account for the early emergence of complex galaxies, rapid chemical evolution, and enigmatic cosmic phenomena. One such avenue of exploration involves rethinking the timeline of cosmic inflation, the rapid expansion phase theorized to have smoothed out the early universe and set the stage for structure formation. JWST's observations of mature galaxies appearing earlier than predicted could imply that inflation ended sooner or operated under conditions unlike those in standard models. This would affect the distribution of primordial fluctuations, potentially explaining the unexpected clustering and size of early galactic systems. Alternatively, some physicists are investigating the possibility that new forms of physics, such as modifications to gravity on cosmic scales, might be at play. If gravity behaves differently in the infant universe, or if additional forces influence matter aggregation, then galaxies could have formed faster and larger than classical theories predict. JWST's precise measurements of galaxy shapes, rotation speeds, and interactions provide critical tests for these novel gravitational theories. Furthermore, the mysterious nature of dark matter, which does not emit, absorb, or reflect light, remains one of the most compelling puzzles JWST helps to probe indirectly. If dark matter particles interact more complexly than currently assumed, they could catalyze rapid star formation by clumping matter more efficiently or even forming dark halos that seeded early galaxy formation in unexpected ways. JWST's mapping of the mass distribution in early galaxies offers new insights into these dark matter properties. JWST also casts fresh light on the enigmatic dark energy that drives cosmic acceleration. By studying distant supernovae, galaxy clusters, and the large-scale structure of the universe, the telescope refines measurements of the universe's expansion rate. Any deviation from the expected value, known as the Hubble constant, could hint at evolving dark energy or new physics beyond the standard model of cosmology. JWST's role in this ongoing effort may eventually clarify whether dark energy is a constant vacuum energy or a dynamic phenomenon linked to the fabric of space-time itself. In addition, JWST's detailed exploration of the epoch of reionization, the time when the first stars and galaxies ionized the hydrogen gas filling the universe, reveals a surprisingly complex and patchy process. Instead of a uniform phase transition, reionization appears to have occurred in bursts and waves, driven by early, bright sources of ultraviolet light and energetic phenomena like quasars. This nuanced picture challenges simplified timelines and suggests that early cosmic environments were more diverse and active than previously thought. The implications extend beyond cosmology and astrophysics into the very nature of time, space, and reality. The more we learn, the more it becomes apparent that the universe might operate according to principles still beyond human comprehension. Concepts like the multiverse, higher dimensions, and quantum gravity gain increasing traction as JWST reveals anomalies and features unexplained by classical theories. Moreover, JWST's contributions to exoplanet science cannot be overstated. By probing atmospheres of potentially habitable worlds, detecting complex molecules, and measuring climate signatures, JWST helps to identify candidates where life might exist or have existed. The early chemical enrichment seen in ancient galaxies suggests that the building blocks of life, carbon, nitrogen, oxygen, and water, were available much earlier in cosmic history than once thought, raising the possibility that life could be widespread and perhaps ancient in the universe. JWST also sharpens our understanding of stellar evolution, supernova mechanisms, and the life cycle of cosmic dust and gas. These elements play vital roles in recycling matter through the cosmos, enabling successive generations of stars and planetary systems to form. The telescope's detailed spectra reveal the intricate interplay of physics, chemistry, and dynamics that create the diverse environments where life's precursors might arise. In confronting these grand cosmic mysteries, humanity stands at a crossroads. The James Webb Space Telescope is not just a window to the distant past. It is a mirror reflecting our insatiable curiosity, our capacity for innovation, and the profound desire to understand our origins and destiny. It challenges dogma, fuels imagination, and invites new generations of thinkers, explorers, and dreamers to engage with the universe in ways never before possible. The mysteries JWST uncovers remind us that science is a journey, not a destination. Each answer begets new questions, each discovery opens new frontiers, and every observation enriches the grand narrative of cosmic evolution. In the end, the quest to understand space, and ourselves, is an eternal adventure, propelled by the human spirit and illuminated by the light of stars that have traveled billions of years to reach our eyes. And so, as JWST continues to peer deeper into the unknown, humanity waits with bated breath for the next revelation, knowing that the universe's greatest secrets may still lie hidden, waiting to transform everything we thought we knew about reality itself. The implications of JWST's findings reach far beyond academic circles. They fundamentally challenge our worldview, touching on profound philosophical and existential questions. If the universe is older, more complex, or governed by unknown forces and cycles beyond the Big Bang, what does that mean for the concept of a cosmic beginning? The notion that the universe had a singular inception event, a moment of absolute origin, has underpinned much of modern cosmology and theology alike. Yet JWST's observations open the door to ideas of an eternal or cyclic cosmos, perhaps one where birth and rebirth of universes are the norm rather than the exception. This shift in perspective encourages us to rethink not just scientific theories, but our place in the cosmic story. Are we a fleeting blip in an endless cosmic cycle, or part of a multiverse of infinite worlds, each with its own laws and histories? The early appearance of complex galaxies and heavy elements suggests the universe has had a far richer history than the simple narrative of gradual structure formation. Life, and perhaps consciousness, could be far more ancient and widespread than previously imagined. Moreover, JWST's discoveries highlight the limits of human knowledge and the evolving nature of science itself. What we hold as fact today may be superseded by tomorrow's revelations. This humility is a core strength of scientific inquiry, constantly adapting and refining our understanding as new data arrives. JWST embodies this dynamic quest, pushing technology and imagination to their limits. The telescope's success also demonstrates the power of global collaboration, combining the efforts of thousands of scientists, engineers, and institutions worldwide. Their work not only advances our understanding of the universe but inspires generations to pursue science, technology, engineering, and mathematics, fostering a culture of curiosity and exploration essential for humanity's future. In the coming years, as JWST continues to explore deeper and with greater precision, we can anticipate even more extraordinary discoveries. Perhaps we will detect the chemical fingerprints of the very first stars, or uncover clues about dark matter's true nature. We might witness the formation of the earliest black holes or discover biosignatures on distant exoplanets, signaling life elsewhere in the cosmos. Each finding will challenge us to rethink assumptions, spark new theories, and deepen our appreciation for the universe's complexity and beauty. In this unfolding narrative, the Big Bang Theory remains a crucial foundation, but it is becoming part of a larger, more nuanced story. JWST invites us to embrace the unknown, to question boldly, and to imagine the cosmos not as a closed book but as an infinite epic, still being written. The mysteries it reveals are not barriers but gateways, inviting us to journey ever onward, propelled by wonder and the unquenchable human spirit. Ultimately, the James Webb Space Telescope reminds us that the quest to understand the universe is a reflection of our deepest aspirations, to know where we come from, how we fit into the grand cosmic scheme, and what lies beyond the horizons of our current knowledge. It is a story of exploration, discovery, and transformation, one that will continue to unfold for decades, perhaps centuries, to come, inspiring humanity to look up, dream big, and seek answers among the stars. Building on this profound transformation in our understanding, it's important to delve deeper into how JWST's data challenges the Big Bang Theory's core assumptions, particularly regarding the timeline and the mechanics of early universe formation. The Big Bang model predicts a gradual emergence of structure, with simple hydrogen and helium atoms slowly coalescing over hundreds of millions of years to form the first stars and galaxies. But JWST's infrared eyes have pierced through cosmic dust in time to reveal galaxies already mature, massive, and surprisingly metal-rich much earlier than these models allow. This suggests that star formation must have been far more rapid and efficient in the early universe than previously thought, or that there might have been alternative pathways to galaxy formation entirely. Some theorists propose scenarios involving primordial black holes, or exotic particle interactions that accelerated matter clumping shortly after the Big Bang. Others are exploring the possibility that the universe did not begin with a singular Big Bang event, but rather underwent a series of cycles, periodic expansions and contractions, or existed as part of a larger multiverse. One intriguing line of inquiry focuses on the unexpected chemical abundances JWST has detected in these early galaxies. Heavier elements, known as metals, in astrophysics, are typically forged in the cores of stars and dispersed by supernovae. Finding high metallicity in galaxies less than a billion years old implies that multiple generations of stars must have formed and died rapidly in a cosmic blink. This rapid, chemical evolution challenges existing timelines and suggests that stellar nurseries operated under conditions we do not yet fully understand. Moreover, JWST's ability to detect the faint glow of the earliest galaxies reveals complex structures, clumps, disks, and spiral arms that appear surprisingly mature. According to classical Big Bang cosmology, such organized structures should take much longer to develop, hinting at new physics or processes at work in the primordial cosmos. Could there be unknown feedback mechanisms from early supermassive black holes regulating star formation? Are there missing pieces in our understanding of dark matter's role in shaping the cosmic web? Another area where JWST is stirring debate is the Hubble tension, the discrepancy between measurements of the universe's expansion rate, the Hubble constant, using local observations versus cosmic microwave background data. JWST's detailed studies of distant supernovae and galaxy clusters provide independent, high-precision measurements that could help resolve this puzzle. The tension may signal new physics beyond the standard cosmological model, such as evolving dark energy or interactions within the dark sector. In addition, JWST's unprecedented sensitivity to mid-infrared wavelengths allows it to probe the universe's cosmic dawn with remarkable clarity. This era, when the first stars and galaxies ignited and began reionizing the hydrogen fog filling space, is pivotal to understanding cosmic evolution. JWST's findings reveal that reionization was a patchy, extended process influenced by varied populations of early galaxies and quasars, complicating the once straightforward picture offered by Big Bang models. The telescope's capabilities also extend to investigating the mysterious dark matter and dark energy that dominate the cosmos. While invisible to direct observation, their gravitational and expansive effects shape the universe's fate. JWST helps by mapping the distribution of mass in galaxy clusters and measuring how light bends around them, testing alternative theories like modified gravity or exotic particle candidates. These insights might eventually redefine what constitutes the fundamental fabric of reality. JWST's discoveries thus weave a complex tapestry that both supports and complicates the Big Bang framework. While the theory remains the cornerstone of modern cosmology, explaining the cosmic microwave background radiation and large-scale structure, the nuances revealed by JWST demand new or revised models that incorporate the rapid emergence of structure, unexpected chemical signatures, and potential new physics in the early universe. As we push deeper, the boundary between known and unknown blurs. Questions multiply. Was the Big Bang truly the beginning, or a transition phase in an eternal cosmos? Could our universe be one bubble in a vast multiverse, each with different physical laws? What unknown forces or particles shaped the first billion years of cosmic history? JWST's ongoing mission promises to illuminate these mysteries, challenging us to expand our theories and embrace the complexity of the universe's grand narrative. In this unfolding cosmic saga, the James Webb Space Telescope stands as humanity's most powerful tool for peering into the universe's earliest epochs and questioning the foundations of our cosmological understanding. Its discoveries inspire awe, provoke new hypotheses, and remind us that the universe is far more mysterious and wondrous than we ever imagined. The James Webb Space Telescope, JWST, has truly revolutionized our view of the cosmos, revealing unexpected details that compel us to rethink the very origin story of our universe. The prevailing Big Bang theory, while enormously successful in explaining many aspects of cosmic history, faces significant challenges as JWST uncovers galaxies that appear astonishingly mature at epochs when the universe was barely a fraction of its current age. This early maturity contradicts the gradual evolutionary process the Big Bang model predicts, suggesting that star formation, galaxy assembly, and chemical enrichment must have occurred at breakneck speed or via mechanisms still beyond our understanding. One striking aspect of these early galaxies is their size and mass. Traditional models posit that galaxies grow hierarchically. Small galaxies merge over billions of years to form larger ones. However, JWST's infrared observations show massive galaxies with well-developed structures only a few 100 million years after the Big Bang. These findings imply either that galaxy formation processes were more efficient, or that some unknown cosmic catalyst accelerated their growth. The chemical composition of these primordial galaxies adds another layer of mystery. Heavy elements like carbon, oxygen, and iron, vital for planet formation and life, are products of multiple generations of stars. JWST's detection of high metallicity in early galaxies indicates that multiple stellar generations already existed, challenging the expected timeline. This suggests that stars formed, lived, and exploded rapidly in the young universe, enriching the interstellar medium faster than standard theories predict. This rapid chemical evolution may also hint at new stellar physics or exotic processes in the early universe. For example, some theorists hypothesize that massive, short-lived stars, known as population 3 stars, may have played a more significant role in shaping early galactic chemistry. These hypothetical stars, composed almost entirely of hydrogen and helium, would burn hotter and faster than later generations, quickly enriching the cosmos with heavier elements through supernova explosions. JWST's findings have also reignited debates about the universe's rate of expansion, a central pillar of cosmology. The Hubble tension refers to the discrepancy between the expansion rate derived from the cosmic microwave background (CMB) measurements and that from local observations of supernovae and galaxies. JWST contributes by providing new, precise distance measurements to faraway galaxies, helping to refine the Hubble constant. If the tension persists, it could indicate physics beyond the standard model, such as evolving dark energy or unknown interactions between dark matter and normal matter. Dark matter itself remains one of the greatest enigmas. Although invisible, its gravitational influence shapes the formation and clustering of galaxies. JWST's detailed mapping of early galaxies helps astrophysicists test competing models of dark matter, including theories involving warm dark matter or self-interacting dark matter, which could explain the unexpectedly rapid formation of large structures. Another frontier illuminated by JWST is the epoch of reionization, the cosmic dawn when the first luminous sources ionized the neutral hydrogen fog that filled the universe. Previously thought to be a relatively swift and uniform process, JWST reveals a more complex, patchy timeline with diverse contributors, including early galaxies and quasars. This intricate picture affects how we understand the transition from a dark, neutral universe to the bright, ionized cosmos we see today. The discovery of surprisingly mature and bright quasars at early times is another intriguing puzzle. These supermassive black holes, millions to billions of times the mass of our Sun, appear to have formed extremely quickly. Their existence challenges models of black hole growth and the coevolution of galaxies, hinting at mechanisms like direct collapse black holes or rapid accretion episodes that remain under investigation. JWST also shines light on the role of cosmic dust in the early universe. Dust grains, formed in the atmospheres of dying stars and supernova remnants, absorb and re-emit starlight, influencing observations and star formation processes. The presence of significant dust in early galaxies suggests complex star formation histories and rapid dust production, requiring new models of dust formation and destruction. Moreover, the telescope's unprecedented sensitivity in the infrared spectrum enables the detection of molecular hydrogen and other key molecules in distant galaxies, shedding light on the cold gas reservoirs that fuel star formation. Understanding the abundance and distribution of this molecular gas is critical for unraveling how galaxies grow and evolve. JWST's contributions extend beyond distant galaxies to the study of exoplanets, where it detects atmospheric components and thermal signatures that may reveal potential habitability. The rapid chemical enrichment indicated in early galaxies suggests that the essential elements for life were available much earlier in cosmic history, raising exciting possibilities for ancient life elsewhere in the universe. The telescope's findings also have profound implications for cosmology's theoretical frameworks. The standard lambda cold dark matter model, which combines the Big Bang with dark energy and cold dark matter, has been remarkably successful, but JWST's observations highlight its limitations and areas requiring refinement. This fuels interest in alternative theories such as cyclic cosmologies, bouncing universes, or emergent gravity, each positing different mechanisms for cosmic origin and evolution. Beyond the scientific community, JWST's discoveries captivate the public imagination, inspiring renewed wonder about the universe's mysteries and humanity's quest to comprehend them. This engagement is vital for fostering support for future missions and the continuation of scientific exploration. Technologically, JWST represents a triumph of engineering and international cooperation. Its complex systems, sunshield, segmented mirror, cryogenic instruments, enable observations impossible from Earth or earlier telescopes, pushing the boundaries of what humanity can achieve in space exploration. The telescope's mission also demonstrates the importance of interdisciplinary collaboration, combining astronomy, physics, chemistry, engineering, and data science to interpret its rich datasets. This integrated approach is essential for tackling the complex questions JWST raises. As JWST continues to operate, its discoveries will likely lead to the identification of new phenomena and perhaps even unknown laws of physics. Each observation refines our understanding of cosmic history, structure formation, and fundamental forces, progressively painting a more detailed picture of the universe. The James Webb Space Telescope is transforming cosmology, challenging the Big Bang Theory's traditional narrative, and opening new vistas for understanding the cosmos. Its revelations about early galaxy formation, chemical enrichment, dark matter, dark energy, and cosmic expansion invite us to rethink our place in an ever more complex and mysterious universe. The journey of discovery it enables is ongoing, promising to reshape our knowledge and imagination for generations to come. The revelations brought forth by the James Webb Space Telescope, JWST, continue to provoke deep reflection on the foundations of cosmology, encouraging scientists to reassess assumptions that have stood for nearly a century. With each new observation, JWST peels back layers of cosmic history, revealing complexities and surprises that hint at a universe far stranger and more intricate than the classical Big Bang framework has suggested. One of the most profound challenges JWST introduces is the apparent early maturity of cosmic structures. Observations of massive, well-formed galaxies at redshifts corresponding to only a few 100 million years after the Big Bang strain conventional timelines. In these nascent epochs, galaxies exhibit disk-like morphologies, prominent stellar populations, and significant metal enrichment, indicators of a complex evolutionary process that seemingly unfolds too quickly. This raises the fundamental question: could the Big Bang model be incomplete or require substantial modification? The Big Bang theory, underpinned by the cosmic microwave background (CMB), radiation, general relativity, and observed cosmic expansion, has long been the backbone of cosmology. Yet the data from JWST forces cosmologists to entertain the possibility that our understanding of the universe's origin, evolution, and composition is still provisional. Some researchers propose that the universe may have experienced phases of accelerated growth or unknown physical processes in its infancy, perhaps driven by phenomena like primordial magnetic fields, exotic dark matter interactions, or even physics beyond the standard model. The JWST's infrared sensitivity allows astronomers to peer through cosmic dust clouds that previously obscured early galaxies, providing an unprecedented glimpse into the cosmic dawn. At this time, the first stars ignited and began reionizing hydrogen atoms that filled the universe, ending the so-called Dark Ages. Contrary to earlier assumptions of a relatively uniform and slow reionization, JWST's observations reveal a patchwork reionization landscape, with bubbles of ionized hydrogen around early galaxies and quasars. This patchiness suggests that the early universe was more heterogeneous, shaped by localized bursts of star formation and black hole activity, leading to a complex interplay of light and matter on grand scales. One of the most captivating discoveries is the presence of supermassive black holes in the young universe. These black holes, with masses exceeding millions to billions of suns, challenge traditional formation theories. The standard paradigm holds that black holes grow slowly by accreting matter or merging with other black holes over billions of years. JWST, however, has found quasars powered by such enormous black holes existing at epochs when the universe was less than 1 billion years old. This rapid growth implies alternative formation channels, such as the direct collapse of massive gas clouds or super-Eddington accretion rates, which defy previous theoretical limits. The telescope has also unveiled unexpected amounts of cosmic dust in early galaxies. Dust plays a crucial role in star formation by cooling gas clouds and enabling them to collapse. The presence of dust so early suggests that star formation was both vigorous and rapid, with multiple stellar generations contributing to dust production. This raises questions about the life cycle of dust in extreme conditions and the efficiency of dust formation mechanisms shortly after the universe's birth. JWST's findings directly impact the ongoing debate around dark matter and dark energy, two of the most mysterious components in the cosmic inventory. Dark matter, which interacts gravitationally but not electromagnetically, is critical to the formation of galaxies and large-scale structure. JWST's detailed observations of the mass distribution in early galaxies and galaxy clusters help test models of dark matter properties, including the possibility of warm or self-interacting dark matter that could alter structure formation timescales. Simultaneously, understanding the accelerated expansion of the universe driven by dark energy is informed by JWST's measurements of distant supernovae and galaxy clustering, potentially offering clues to whether dark energy is constant or dynamic. Another domain where JWST is shedding light is the origin and evolution of the first stars, known as population 3 stars. These primordial stars, formed from pure hydrogen and helium, have long been hypothesized but never directly observed. They are thought to have been massive and short-lived, initiating the first steps in cosmic chemical enrichment. While JWST has yet to confirm definitive population 3 star detections, it has identified candidate galaxies and star-forming regions that exhibit unusual spectral signatures possibly linked to these early stars. Confirming their existence and properties would fill critical gaps in understanding how the universe transitioned from simplicity to complexity. Beyond galaxies and stars, JWST's capabilities extend to the intergalactic medium, IGM, the diffuse gas between galaxies that holds the majority of the universe's baryonic matter. The IGM's ionization state, temperature, and chemical composition provide crucial context for the evolution of cosmic structures. JWST's observations of absorption lines in the spectra of distant quasars enable detailed studies of the IGM's properties, revealing how galaxies and black holes influence their surroundings through radiation, winds, and supernova explosions. The telescope's contributions also enhance our understanding of galaxy morphology and kinematics in the early universe. By analyzing how stars and gas move within young galaxies, astronomers can infer the presence of dark matter halos, the impact of feedback from star formation, and the role of mergers in shaping galactic evolution. JWST's high-resolution imaging and spectroscopy provide data that challenge simple hierarchical growth models, suggesting that galaxy assembly is a far more dynamic and varied process. Furthermore, JWST's detection of molecular hydrogen, carbon monoxide, and other molecules in early galaxies sheds light on the cold, dense phases of the interstellar medium crucial for star formation. The abundance and distribution of these molecules inform models of how gas cools and collapses into stars, particularly under the extreme conditions of the early universe where radiation fields, metallicity, and cosmic rays differ markedly from today. JWST's observations also prompt reconsideration of the initial conditions of the universe itself. The cosmic microwave background offers a snapshot of the universe approximately 380,000 years after the Big Bang, but JWST pushes this window closer to the first billion years. If the early formation of large, metal-rich galaxies is confirmed, it may imply that density fluctuations in the primordial universe were larger or behaved differently than predicted by the inflationary models underpinning the Big Bang theory. Additionally, some theorists speculate that JWST's findings could be consistent with alternatives to the singular Big Bang event, such as the cyclic or ekpyrotic universe models. These theories propose that the universe undergoes endless cycles of expansion and contraction, or that our universe was born from the collision of higher-dimensional brains. JWST's evidence for accelerated early structure formation might be naturally explained in these contexts, which allow for more complex pre-Big Bang histories. The continued influx of data from JWST ensures that cosmology is entering a new era of precision and complexity. Models that once comfortably described the universe now face the challenge of integrating these rich, sometimes contradictory observations. This process is emblematic of scientific progress, where theories evolve, adapt, or give way to new paradigms as evidence accumulates. Moreover, JWST's discoveries have profound philosophical implications. The earlier availability of heavy elements and complex structures suggests that conditions for life's building blocks existed much sooner than expected. This extends the temporal window during which life might arise in the universe, stimulating astrobiological investigations and considerations of humanity's cosmic context. JWST also exemplifies the power of human ingenuity and international collaboration. Developed over decades through partnerships between NASA, ESA, and CSA, the telescope embodies a collective ambition to peer deeper into the cosmos. Its success highlights how large-scale scientific endeavors transcend national boundaries and unite diverse expertise toward common goals. The telescope's mission is far from complete. As it continues to survey the skies, JWST will undoubtedly uncover more anomalies and phenomena that challenge conventional wisdom. Each discovery provides not only answers but also new questions, driving a continuous cycle of exploration and understanding. Ultimately, JWST's legacy will be defined by its role in transforming cosmology from a theory-dominated science into an observation-driven one, where data guides and constrains theoretical frameworks. This shift promises richer, more nuanced models of the universe's origin, composition, and destiny. In this unfolding narrative, the James Webb Space Telescope acts as a cosmic lighthouse, illuminating the unknown and inviting humanity to contemplate its place in an ever-expanding, mysterious universe. Its discoveries inspire wonder and humility, reminding us that despite our advanced technology and theories, the cosmos still holds secrets beyond our current grasp. As we reflect on JWST's profound impact, it becomes clear that the story of the universe is not a closed book but a living saga, one written in the light of distant stars, the whisper of ancient atoms, and the tireless quest for knowledge that defines us as a species. The telescope's revelations herald a new chapter in this epic, inviting us all to join in the journey of cosmic discovery. And as this journey continues, we begin to see that the implications of the James Webb Space Telescope's observations go far beyond merely tweaking a few parameters in existing models. They strike at the very heart of the assumptions we've held for decades about the timeline, composition, and even geometry of the universe. One especially disruptive revelation comes from the detection of galaxies that, by all current measurements, appear far too massive, too luminous, and too evolved to have formed in the brief time allowed by the standard Big Bang cosmology. For instance, when astronomers used JWST to observe galaxies at redshifts greater than 10, which corresponds to a time when the universe was only a few 100 million years old, they're often met with galaxies that shouldn't exist yet. These aren't dim smudges of barely organized gas and stars. Rather, they are bright, massive, and fully formed systems with clear structural integrity. In standard cosmological simulations based on lambda cold dark matter theory, such galaxies are not predicted to exist this early. To accommodate these findings, scientists are being forced to stretch current models to their breaking points, introducing exotic new physics or revising assumptions about star formation efficiency and initial mass functions. Another surprising element of JWST's data is the discovery of an abundance of high redshift galaxies. Initial models predicted that galaxies would be sparsely distributed at redshifts beyond 10, due to the limited time available for them to form. But instead, JWST is seeing far more of these ancient galaxies than expected, and not just faint ones, but large, bright, and complex structures. This has prompted some cosmologists to revisit the assumptions about the expansion rate of the early universe, or even to question the calibration of redshift as it relates to time and distance under current cosmological interpretations. These observations have ignited discussions about the possibility that the redshift-distance relationship, a cornerstone of the expanding universe model, might not be as linear or straightforward as we believed. While the standard interpretation of redshift is that it indicates how fast objects are receding from us due to cosmic expansion, alternative theories posit that some redshift might result from other mechanisms, such as intrinsic redshifts tied to the properties of the galaxies themselves, or interactions with intervening cosmic media. While such theories have been on the fringes of astrophysics for years, JWST's surprising results are giving them renewed attention. It's not just the age or size of these early galaxies that baffles scientists, it's also what they contain. Metals, elements heavier than helium, should be rare in the early universe. They are formed in stars and spread into the cosmos through supernova explosions, a process that takes many generations of stars over hundreds of millions of years. Yet, JWST has found galaxies rich in metals almost as soon as the universe began. This calls into question the speed of early star formation and the entire timeline of cosmic chemical evolution. Either star formation began much earlier than we thought, or the first stars lived and died in spectacularly fast cycles to enrich their host galaxies in record time. Additionally, these findings have sparked interest in exotic early universe phenomena, such as primordial black holes. These hypothetical black holes could have formed directly from density fluctuations in the very early universe, independent of stellar evolution. If they exist, they might have seeded the formation of galaxies, accelerated structure formation, and even contributed to the apparent overabundance of early massive objects. JWST might not be able to detect primordial black holes directly, but its observations could provide indirect evidence for their existence by revealing the gravitational effects they exert on surrounding matter. Another intriguing hypothesis being revisited is that of a bounce cosmology. Unlike the traditional Big Bang model, which posits a singular origin point from which the universe has been expanding ever since, bounce models suggest that the universe undergoes periodic cycles of contraction and expansion. In such models, the universe could have been populated with complex structures and high metallicity even before the current expansion phase began. The anomalies JWST has found might be relics from a previous cosmic cycle, a possibility that would profoundly alter our view of the universe's origin. Even more radical theories are now entering serious discussions among cosmologists, such as the simulation hypothesis. The idea that the universe is a kind of programmed environment or simulation has long been a fringe idea. However, the peculiar regularities and seeming violations of expected physical law in JWST's data have led some to reconsider whether we're seeing glitches or artifacts that could suggest a deeper, hidden architecture beneath what we perceive as physical reality. Adding fuel to the fire is JWST's extraordinary ability to analyze the atmospheres of exoplanets. While this may seem unrelated to cosmology at first, the implications are vast. Discovering biosignatures or chemical disequilibrium in the atmospheres of ancient exoplanets could suggest that life, or at least the conditions for life, emerged far earlier in cosmic history than expected. This would further compress the timeline for complexity to emerge, aligning with the broader trend of JWST revealing a universe that matures too quickly to fit the standard model. Compounding these discoveries is the problem of cosmic isotropy. The Big Bang Theory assumes that the universe is roughly the same in all directions, a condition known as isotropy. Yet JWST's deep field surveys have revealed significant asymmetries in the distribution of galaxies and their types across the sky. Some sectors of space seem to harbor more early galaxies, or different types of galaxies, than others, raising questions about whether the early universe was truly homogeneous and isotropic. If confirmed, this would necessitate a reevaluation of the cosmological principle, the bedrock assumption that underpins virtually all modern cosmological models. The telescope is also providing new data on gravitational lensing, which occurs when massive objects like galaxy clusters bend and magnify the light from more distant objects behind them. JWST's sensitivity allows it to detect extremely faint galaxies that have been magnified through lensing, offering glimpses of structures that might otherwise be invisible. In some cases, the magnified galaxies appear significantly older and more developed than anticipated. These lensed observations provide further evidence that the early universe may have hosted a diverse population of galaxies, each evolving on different, accelerated timelines. Some scientists argue that to reconcile these observations with theory, we must embrace a more dynamic conception of spacetime itself. The classical view holds that space and time are passive backdrops against which matter evolves. But what if spacetime is emergent, rising from more fundamental, quantum mechanical processes? This view is gaining traction in theoretical physics, particularly in the context of quantum gravity. JWST's data might serve as an empirical testing ground for such revolutionary ideas, if scientists can correlate observable phenomena with predictions made by these emerging theories. Another paradigm under scrutiny is cosmic inflation, the idea that the universe underwent a rapid expansion shortly after the Big Bang. Inflation was introduced to explain several cosmological puzzles, such as the horizon and flatness problems. However, JWST's findings cast doubt on whether inflation alone can account for the complexity and structure observed at high redshifts. If inflation did occur, it may need to be revised to include far more complex behaviors, or it might be replaced altogether by a different mechanism, such as string gas cosmology or holographic scenarios. Ultimately, what JWST is doing is reshaping the contours of the possible. It is telling us, in no uncertain terms, that the early universe was not the simple, orderly place we once imagined. It was a chaotic crucible, teeming with matter, energy, structure, and complexity far sooner than any model predicted. This revelation is both exhilarating and humbling. For every answer JWST provides, it opens up a dozen new questions, each more profound than the last. As data continues to stream in from this remarkable observatory, one thing is becoming increasingly clear: we are witnessing the dawn of a new era in cosmology. Not an era defined by certainty, but one characterized by curiosity, bold ideas, and a willingness to question everything we thought we knew. The universe, it seems, still has secrets to share, and the James Webb Space Telescope is just beginning to unlock them. This unfolding cosmic narrative, catalyzed by the James Webb Space Telescope, is beginning to feel less like a refinement of known science and more like a rebirth of cosmological thought itself. As the telescope peels back the ancient layers of the universe, it's as though we are encountering not just a different time, but a different set of physical rules entirely, an era where the classical understanding of gravity, time, space, and energy might not apply in the ways we have come to expect. One of the most pressing questions arising from JWST's discoveries is whether the fundamental constants of physics were actually constant in the early universe. This is a radical proposition, but it could help explain the abundance of massive galaxies, high metallicity, and mature structures seen just a few 100 million years after the supposed Big Bang. If constants like the gravitational constant, g, the speed of light, c, or the fine structure constant, alpha, varied slightly in the early cosmos, the rate of structure formation could have been significantly different, possibly much faster than predicted. There are theories in physics that suggest such variability is possible, and JWST's data might be the first observational push towards seriously considering these models. We're also seeing fresh interest in the concept of early dark energy. This idea proposes that a form of dark energy existed much earlier in cosmic history than currently believed, potentially acting as a repulsive force that shaped the rate at which matter clumped together. In standard models, dark energy only becomes significant billions of years after the Big Bang, driving the current acceleration of the universe's expansion. But if it had an early phase, even a brief one, it could help explain the accelerated development of structure observed by JWST. The data has made it clear that the early universe was not a slow, gradual unfolding. It was a furnace of rapid formation, a cosmic flashpoint in which the rules of engagement may have been different. A further layer of mystery emerges from JWST's infrared spectroscopic capabilities, which allow astronomers to probe the chemical fingerprints of early galaxies in exquisite detail. By analyzing these spectra, scientists can determine not only the age and composition of galaxies, but also the temperature and velocity of their interstellar gases. What's emerging from this data is a picture of galaxies with shockingly mature chemical complexity. Molecules like carbon monoxide and even hints of water vapor have been detected in galaxies so ancient that the atoms within them may have formed within the first generation of stars. These findings, if verified, dramatically compress the timeline for star formation, supernova feedback, and chemical enrichment, processes once thought to take hundreds of millions or even billions of years. Beyond the galaxies themselves, JWST has begun to offer a deeper look at the cosmic web, the vast, large-scale structure of the universe composed of filaments of dark matter and gas. While still in early stages, these observations may soon offer insights into how matter clustered into galaxies and galaxy clusters under the influence of gravity. Already, we are seeing indications that the cosmic web may have formed earlier and in denser configurations than predicted. This too challenges the notion of a gradually cooling, expanding cosmos, and suggests a universe that was ready for complexity from the very beginning. What if, as some theorists are now wondering, the Big Bang was not the singular origin of everything but merely a phase transition in a much larger and more complex universe? This idea has begun to gain traction in the wake of JWST's discoveries, especially as some models suggest that the universe may have existed in a different state, a more symmetrical, higher-energy vacuum, before undergoing a phase shift that produced the universe we now observe. In such scenarios, what we call the Big Bang is not a beginning, but a boundary between epochs, like the surface of a boiling liquid as it shifts to vapor. This could explain why structure seems to have formed so rapidly. It wasn't starting from scratch. Another bold theory gaining renewed attention is conformal cyclic cosmology, CCC, proposed by Sir Roger Penrose. This model suggests that the universe undergoes infinite cycles or eons, each ending in a vast stretch of expansion followed by a transformation into the conditions suitable for the next aeon to begin. In CCC, the Big Bang is just the bridge between two eons, and structures from the previous aeon could leave imprints on the next, perhaps even accounting for some of the unexpected structures JWST is now detecting. Although controversial, CCC aligns intriguingly with a cosmos where galaxies and complexity seem to emerge far too early to be explained by linear timelines alone. Of course, JWST isn't the final word on any of these matters, it's just the beginning. The telescope's mission has only just begun, and its observations will span a decade or more. But already, the findings have triggered a deep existential reevaluation of the nature of reality itself. What if time, as we understand it, is not linear? What if cause and effect, so essential to the Big Bang model, are emergent phenomena rather than fundamental properties? Quantum theories of gravity, such as loop quantum gravity and string theory, have long suggested that spacetime itself is not continuous but discrete and emergent. JWST might be providing the observational evidence that such frameworks need to gain mainstream acceptance. And let us not forget the philosophical implications. For centuries, humanity has sought to understand its place in the cosmos by building narratives. The Big Bang has been our dominant cosmological narrative for the past century, providing a neat origin story with mathematical rigor. But what happens when the evidence begins to undermine the very core of that narrative? The psychological weight of that realization is immense. It suggests we may be on the verge of a new cosmological revolution, not unlike the shift from the geocentric to the heliocentric model of the solar system. The role of technology in this revolution cannot be overstated. JWST is not merely a better telescope, it's a portal through which we are glimpsing a previously invisible universe. With its unmatched infrared sensitivity, it reveals the oldest light, the faintest galaxies, and the most ancient secrets of the cosmos. But perhaps more importantly, it is teaching us the limits of our knowledge. Every surprising galaxy, every inexplicable chemical signature, every impossible structure, it all tells the same story. We don't know as much as we thought we did. And in that realization lies a profound beauty. Because science, at its core, is not about certainty. It's about wonder. It's about asking questions so bold that they threaten the very foundations of what we believe to be true. The James Webb Space Telescope, like Galileo's telescope before it, is a radical invitation to rethink everything, and to embrace the mystery. As the universe reveals its secrets layer by layer through the eyes of the James Webb Space Telescope, we find ourselves standing at the edge of a cosmic paradigm shift. The confidence in the Big Bang as the ultimate origin story is beginning to show cracks, not from speculative theory, but from tangible, peer-reviewed data pouring in from the deepest reaches of space. Each new observation seems to echo a common theme. The early universe is older, more complex, and more structured than the Big Bang model allows. One of the most stunning realizations has been that we are seeing galaxies, fully formed, mature, and massive, at epochs where, by standard cosmological models, such objects should not yet exist. These aren't vague smudges or statistical anomalies. They are bright, clear, and chemically enriched islands of stars that challenge everything we thought we knew about cosmic chronology. If these galaxies existed just 300 to 400 million years after the alleged Big Bang, it raises the question, how did so much organization, so much stellar activity, happen so fast? The problem is not just speed. It's the impossibility of timing. In the lambda-CDM model, the current standard cosmological framework, the growth of structure is a slow, stepwise process. Tiny fluctuations in the cosmic microwave background (CMB) radiation serve as seeds for gravitational collapse, gradually forming stars, then galaxies. But JWST is showing us a universe where this process seems to be fast-forwarded. It's like walking into a movie expecting the first act, only to find you're already in the final scene. And the anomalies don't stop at galaxies. In several observations, astronomers have detected supermassive black holes, millions or even billions of times the mass of our Sun, lurking at the centers of ancient galaxies. These monsters weren't supposed to form until long after the first stars and galaxies emerged. According to theory, it takes a significant amount of time for black holes to grow by feeding on gas and merging with other black holes. Yet here they are, massive and mature, already anchoring the centers of galactic cores at redshifts higher than 10. This leads to an even stranger implication. If galaxies and black holes were this well developed so early, could it be that the Big Bang timeline is fundamentally flawed? Could we be misinterpreting redshift, our primary tool for estimating cosmic distances and ages? Some researchers are now considering alternative interpretations, like intrinsic redshift, where light might be stretched not just by cosmic expansion but by other, less understood mechanisms. It's speculative, yes, but the data demands that we at least entertain these possibilities. And what about the composition of these galaxies? JWST's spectrographs have detected elements like oxygen, carbon, and even hints of nitrogen, elements that should have required several generations of star formation and death to accumulate. In the standard model, early stars were almost entirely hydrogen and helium. Only after many cycles of stellar evolution would heavier elements, what astronomers call metals, begin to appear. But JWST is already detecting galaxies with surprisingly high metallicities, indicating a complex history that the current timeline simply doesn't allow. Further complicating the matter is the fact that some of these ancient galaxies appear to be disc-shaped, structured and rotationally stable. This too is unexpected. According to cosmological simulations, galaxies in the early universe should have been irregular and chaotic, gradually settling into more organized forms over billions of years. But JWST is showing elegant spiral-like structures appearing too soon, too smoothly, to be explained by hierarchical models of galaxy formation. One possible interpretation gaining traction is that the Big Bang wasn't a unique explosion from a single point, but rather a localized event, or one of many such events, in a much larger cosmological landscape. This concept is supported by ideas from eternal inflation and multiverse theories, where bubble universes like ours are continually forming within an ever-expanding meta-universe. In such a framework, the notion of a singular beginning becomes irrelevant, and the existence of mature galaxies early on could simply be an artifact of a different pre-Big Bang history leaking into our observations. Another avenue of research is examining the implications for dark matter and dark energy, the two mysterious entities that supposedly make up 95% of the universe's contents. If the distribution and behavior of matter in the early universe are not matching predictions, maybe our understanding of these invisible components is deeply flawed. Perhaps dark matter isn't a particle at all, but an emergent phenomenon or even a misinterpretation of gravity at cosmological scales. Modified gravity theories, like modified Newtonian dynamics, or emergent gravity, are being revisited in light of these findings. Moreover, JWST's unexpected revelations are beginning to question the foundational role of the cosmic microwave background radiation itself. The CMB has long been considered the afterglow of the Big Bang, a snapshot of the universe 380,000 years after its supposed origin. But if galaxies and complex structures existed far earlier than that, then the timeline linking the CMB to large-scale structure formation becomes incoherent. Some fringe cosmologists are even speculating whether the CMB might be a relic of something else entirely, perhaps a cyclical universe, a bounce from a previous cosmic contraction, or a horizon signature of a larger dimensional space. The implications also spill over into quantum cosmology. JWST's data may offer indirect support for theories suggesting the universe began in a quantum state of timelessness. This idea, supported by the Wheeler-DeWitt equation in quantum gravity, posits that the universe existed in a static, timeless quantum configuration before collapsing into the dynamic, expanding cosmos we now observe. If so, the Big Bang wasn't a bang at all, but a phase transition from timeless quantum fuzz to temporal classical expansion. Such models can accommodate the early complexities seen by JWST without requiring vast stretches of time. What we are witnessing is more than just an observational discrepancy. It's a foundational dissonance between theory and evidence. Cosmologists are being forced to return to first principles, to question the very bedrock of assumptions upon which the last 100 years of astrophysics have been built. And this is no small thing. It affects everything from our understanding of time and entropy to the very idea of causality in a relativistic framework. All of this culminates in one profound truth: JWST is not just a telescope, it is a philosophical device. It doesn't merely extend our vision, it challenges our understanding of existence. It throws into doubt the simplicity of our origin stories and compels us to confront a universe that is stranger, older, and more mysterious than we dared imagine. And yet, amid all this uncertainty, there's a kind of wonder, a cosmic humility that reminds us we are still infants peering into the cradle of the cosmos. Every image from JWST is a lesson, a whisper from the ancient universe inviting us to rethink, to relearn, to rediscover the story of everything. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.